Okay. We start the third day of our conference. We start the third day of our conference in memory of Boris Dubrovin. The first speaker is Sergey Lando, Higher School of Economics and School Tech. Real Hurwitz numbers, please.
Thanks, Oleg, and it would be a real pleasure for me to give a talk at such a conference, but unfortunately, we have to say goodbye to our friend and colleague Boris Dubrovin, and my talk will be dedicated not only to his memory, but also to the memory of Serежа Natanzon. We lost him last year, almost a year ago, and the two were friends and colleagues and very close friends, and they shared a long history of their relationship. Both are lost untimely. They shared common papers, well-known papers on finite gap potentials in integrability, and both served for the independent university. Boris Dubrovin is one of the founders of the independent university, and Serежа gave about 20 years of his life to the independent university, or maybe even more. And it's very hard to understand that they are not with us any longer. And my talk will be based on our only joint paper with Serежа and Maxim. This is only the starting point of the future research, but this will not be conducted together with Serежа. So I will speak mainly about real Hurwitz numbers, but let me start with complex ones. A lot is known about complex Hurwitz numbers, and they are an important instrument in understanding the geometry of the modular space of curves, while much less is known about real Hurwitz numbers, and which makes them an interactive subject of study. Now, what we do know about complex Hurwitz numbers? First of all, what are complex simple Hurwitz numbers? These are numbers enumerating neuromorphic functions functions on algebraic curves such a number is Hm mu, where mu is a partition describing ramification over infinity and m is the number of simple critical points. Simple critical points. So the adjective simple in the name of the talk refers to the case when there is only one complicated ramification, only one potentially degenerate ramification, the ramification over infinity, while all the other ramification types are just simple. And these Hurwitz numbers are related to the Frobenius algebra, which defines the cohomological topological field theorem. Topological field theorem. Field theory. And this field theory is very simple. The corresponding Frobenius algebra is the center of the group algebra of the symmetric group, which is a subalgebra in the group algebra of the symmetric group. And this is a kind of topological field theories. It was invented as one of the first examples of topological field theories. One can collect all the Hurwitz numbers into a huge generating function. Depending on infinitely many variables, plus one. It depends on a variable u and a sequence, an infinite sequence of variables pi, which is the sum over all m and mu h m mu p mu1, p mu2, and so on, u to the power m over m factorial. Mu is the partition, as I have said already. It consists of parts mu1, mu2, and so on. And the corresponding variables are in charge of the length of the cycles in permutations in the symmetric group Sn. In the symmetric group, we take a permutation and we consider its decomposition into a product of independent cycles. The cycles are the length of the cycles are uniquely determined by the permutation. And this permutation is the monodromy of our meromorphic function over infinity. So we obtain such a huge generating function, which covers all the information about Hurwitz numbers, about complex simple Hurwitz numbers, and this function satisfies the so-called cut and join equation. Cut and join equation due to Goulden and Jackson. Around 1994. This equation has the form of an evolution equation. The derivative of h with respect to u is the result of applying to u the operator w. This is a partial differential operator, which is essentially the Calogero-Moser operator. Moser operator, which looks like W is equal to 1/2 of the sum over all I and j, pi plus j, pi plus pi pj d over dp I plus j plus pi plus j d2 over dpi dpj. So there is a natural non-degenerate scalar product on the algebra.
And what is the geometric meaning of this equation?
The meaning of this equation here is combinatorial. Why it is called cut and join equation? We take a permutation and multiply it by a transposition. And we look what happens with the lengths of the cycles, of the independent cycles in the permutation. There are two possibilities. Either two cycles of length I and j are glued together by a transposition, so that we obtain a single cycle of length I plus if you let me answer first Sasha's questions.
So you put the coefficients I plus j and
There should be coefficients, yeah. I plus j is, yeah, I plus j, you're right. And ij here. Sorry. The other possibility is that the two permuted elements belong to one and the same cycle of length I plus j, and the cycle splits into two cycles of length I and length j, respectively. If you write the Calogero-Moser operator, which is usually written in variables xi, if you rewrite it in terms of power sums of the variables xi's, if you put here
is it quantum proportional?
it's k to the power n, then you will obtain exactly this operator. Just ordinary collateral. Classical collateral. Yeah. Quantum. It's a differential. Yeah. Yeah, what I wanted to say is that there is a natural scalar, non-degenerate scalar product on the center of the group algebra of the symmetric group, and with respect to this product, W is a self-adjoint operator. Therefore, it is diagonalizable. And in 2000, Konkov.
So I don't understand in what sense it is an operator.
In fact, homogeneous polynomials in the variables pi are identified naturally with the center of the group algebra, the space of homogeneous polynomials of degree n, where we set pi equal to n, to I, for all I. Then the space of homogeneous polynomials of degree n is naturally identified with the center of the group algebra. So that the center of the group algebra, it is generated by these are Newtonian polynomials. Yeah. No SNP. We just need all Sn for all n, for each n.
Just the union.
Just the union, yeah. And the operator W splits into a direct sum of operators acting separately on the spaces of homogeneous polynomials in the variables pi. So, and Okounkov has shown that Schur polynomials form an eigenbasis for W, and he also computed the corresponding eigenvalues. And using this data, he deduced that W is a tau function for the KP hierarchy, for the Karamtsov-Petriashvili hierarchy of partial differential equation. So, in addition, we know that the coefficients of the logarithm of the function h are closely related to the geometry of moduli space of algebraic curves. Given bar.
It's not clear how W as a operator can be a function. It's very H. No, third line.
Not W, sorry. Of course, H. I meant. Thanks, Alec. So the coefficients of the logarithm of h that enumerate connected, that enumerate meromorphic functions on connected algebraic curves are closely related to the geometry of moduli spaces of algebraic curves, via the ELSV formula (1999), and using this two information, Maxim Kazaryan and me, we proved, gave an algebra geometric proof of Witten's conjecture. Geometric proof of Witten's conjecture So what about real Hurwitz numbers? Real Hurwitz numbers enumerate meromorphic functions on real meromorphic functions on real algebraic curves. And we would like, sorry? It is real in the following sense. There is an automorphism of CP1 to CP1, which is just the complex conjugation, and we consider curves having. What is a real curve? A real curve is a complex curve endowed with an involution, which is a complex anti-holomorphic involution. And we consider mappings that are equivariant with respect to this pair of involutions. So these numbers, I will denote them HR and mu. Also, we have some ramification over infinity, and we have m simple critical points. But now the ramification over infinity is much more the data mu containing the ramification type over infinity is much more complicated than in the case of complex numbers. It contains 4 types of partitions: kappa, kappa plus, kappa minus, and lambda, which indicate precisely the following ramification data. Ramification data. The ramification data is, these are orders of poles of, let me just call them odd poles. These are orders of positive even poles. So that we have poles like that here. These are the same, but for negative even poles. And these are complex conjugate poles. No, the ramification over infinity is complicated. It could be complicated. It is allowed to be complicated. All these are partitions. So that together they form a partition of the degree of our meromorphic function.
So now we need to double that.
Yeah, exactly. Exactly. And so that when we produce a generating function, let me put it number 3, generating function. Function HR. It depends on variables of 4 types: P1, P3, and so on. Then P2 plus, P4 plus, and so on. P2 minus, P4 minus, and so on. And Q1, Q2, and this is just the sum over all m and mu, h m mu r p kappa 1, p kappa 2, p plus kappa 1 plus, and so on.
So we don't split simple poles according to the
we have a variable q, variables q are in charge of complex conjugate poles.
no, I'm talking about simple ramification. So you don't care whether they are real.
Simple ramification points are necessarily real, because otherwise they would not be simple. If you have two complex conjugates, then you have a double critical value taken at this complex conjugate point. Sorry, we simply do not allow. We require that all the critical points are real.
So that's an additional assumption.
That's an additional assumption. There are. It happens that there is a Frobenius algebra which is in charge of the behavior. Let me put it into make it like that. It's not strictly a Frobenius algebra, which looks like follows. By a state on consisting of n elements, we mean an involution of this set. And a transition is a pair of states. A pair of states which could be drawn like that. Something like that. 1, 2, 3, 4. 1, 2, 1, 4, 2, 3. So on the state in the left, we have 1 and 2 are transposed by the involution, while 3 and 4 are two fixed elements of the involution. And on the right, we have an involution which takes which exchanges 1 and 4 and 2 and 3. This is S1, this is S1, this is S2. Tn is the algebra of transpositions of white transpositions of transitions. Where we define a product of two transitions to be S1, S2 times S1 prime, S2 prime to be equal to S1, S2 prime, provided that the two intermediate states are the same. S1 prime and 0 otherwise. This algebra, the algebra of transitions, plays the role of the group algebra of the symmetric group. for the real case, and this algebra contains the subalgebra AN, which is the subalgebra of elements symmetric with respect to permutations of our set and consisting of n elements. Well, this algebra also has a non-degenerate scalar product. Scalar product. And there is an operator which is an analog of cut and join operator. There is a cut and join operator WR, so that the generating function for real Hurwitz numbers is subject to the evolution equation defined by this operator. The operator is similar to the one drawn on the left, but now it is more complicated because it depends on four sequences of variables rather than a single sequence. This operator, similarly to the complex case, is a self-adjoint operator with respect to this scalar product. Is self-adjoint. Is a self-adjoint operator, and therefore it is diagonalizable. Unfortunately, at this place, the situation is more complicated than in the case of the complex cut and join operator, because the diagonalization is not that obvious. It's
sorry, with respect to a product or a pairing?
Sorry?
Sorry, with respect to a product or a pairing?
With respect to the scalar product. With
Okay.
respect to the scalar product I've mentioned. I have not defined it. I just said that there is a scalar product.
But no bilinear form.
Is it a bilinear form?
Well, I mean, in the usual Frobenius algebras, there is also the pairing, and here not.
Yeah, it behaves well with respect to the multiplication.
Oh, thanks.
Okay, in this sense, yeah. Yeah, but there is no such beautiful basis of eigenfunctions as in the case, in the complex case. In this case, we have the set of Schur polynomials, and we know the corresponding eigenfunctions. And it happens that there are eigenfunctions, but they are more complicated than the Schur polynomials. However, it is possible, nevertheless, to effectively compute real Hurwitz numbers, by studying the representation of the symmetric group on the algebra of transitions, induced by its action by permutations of the set of n elements, which I do not have time to speak about in more detail. But here we are before the most interesting part of the future study, probably. One can hope that there is a close relationship between real Horvitz numbers and the geometry of real algebraic curves, which is not discovered yet. And it was a dream of Serezha Natanzon that such a relation can be found, and the understanding of geometry of moduli spaces of real curves can be obtained through real Horvitz numbers. Let me stop here. I do not have more time.
Thank you, Sergey. Let's thank the speaker. And, first question from audience. Do we have questions from Zoom? No? Okay. I have a small remark. Certainly, your remark that W is Lager's motor operator is very interesting, but certainly needs explanation. Because normal Lager's motor operator is in finite number of variables. So this operator probably corresponds to infinite symmetric group or infinite full linear group, something like that.
What I have mentioned is that this operator is a direct sum of finite dimensional operators. Each finite dimensional operator in the space of polynomials of given degree.
I would better believe that it's perfect. Of normal.
Okay.
Any questions? So let's thank Sergey again. We have break for half of an hour until 12:10. resume our session. The next speaker is Maxim Kazaryan, High School of Economics and Skoltech, topological recursion for generalized Hurwitz numbers.
Thank you. I remember while I was a postgraduate student, I was in somewhere in the middle of 90s, I visited Bochum University, and I observed in my office some number of copies of preprint. And this preprint was the preliminary version of the book by Boris Dubrovin on Frobenius manifolds. I just took this preprint for peculiarity, and I observed it was very interesting. But now we know that this book changed dramatically the whole theory of Frobenius, of Gromov-Witten theory and integrable systems. And this was my first experience when I met the integrable system theory. But then I had a lot of nice conversation with Boris, and his works influenced me a lot. So I will also speak on kind of integrable, some subject of integrable system, namely topological recursion. Everybody knows that the word, the very term integrable system has many different meanings, and the topological recursion is one of the just different language also to describe some integrable properties. And it is different very much from in its very form, it's different very much from what we usually know about integrable systems like differential equations. And in a sense, topological recursion can be regarded as a certain reformulation of Virasoro constraints, but the form it is usually represented is quite different. And nowadays it appears somewhere about 10 or 15 years ago. Now it's become more and more popular. There are conferences, books, a lot of papers, but still it somehow looks like a miracle. The very fact that it works in many situations usually considered as a miracle. So the goal of my talk is not only to prove, but somehow to explain what is the meaning of topological recursion. I know many people who heard a lot and listened to a lot of talks on this subject, but still very surprised about the very notion of topological recursion. So I will present my own point of view to topological recursion. And this is just one of the versions, so-called global version with rational spectral curve. So what it is about? So we have some number of quantities, fg, k1, kn, which are labeled by an integer g called genus, and also partition k1, kn. And they could be of different origin, from combinatorics or matrix integrals or Gromov-Witten theories. There are many different situations where this kind of numbers appear in mathematical physics and in combinatorics. And the goal is just to compute these numbers. So there is a way to collect them in a single generating series called potential. This potential depends on an infinite number of variables, and these quantities appear as Taylor coefficients of this series. And this kind of potential usually possess a lot of nice integrable properties, like integrable hierarchy equations or Virasoro constraints and so on. And this is what's called in Gromov-Witten theory, it's Frobenius potential, or in mathematical physics itself.
Do they converge or not, the series? Do the series converge or not?
Well, it's infinite number of, there is infinite number of variables. There is no even way to think.
If you assume that only finite combination, only finite number of variables, you can assume that you have only finite kn and then all other are zero.
Probably.
Think about these quantities, then
So, but assume that, but at least it's possible to prove conversions at least somewhere.
Well,
if all these quantities are zero,
No, not zero. But for example, Q1 is not zero.
so in one sense, it seems to be senseless to speak about convergency because I speak about combinatorics and I consider it just as a formal series. But as we will see, the convergency property is very important when we look at the different way to collect them in the genetic series. So there is a different way to collect them in a series when we put instead of indices ki's, I use just exponents of the new variables. And then when we compose such a series, the convergency really plays an essential role in what I will speak about. And I will discuss it later. So I will speak about convergence in the context of this series, endpoint function.
and is your partition ordered?
No, the invariant with respect to permutation of ki's.
But then, I mean, for the correlator function, how do you choose which variable you?
So it's this series symmetric. No. It's these numbers I have not written, but they should be symmetric. It depends only on the partition.
So there is a kind of hidden symmetrization.
Yeah. So let me give you just an example of what kind of series I will consider. So I will just consider elementary combinatorial examples. So one of the first cases is the enumeration of maps. It appears also in the so-called two matrix models. So we have a map, a graph embedded to a surface such that the complement of each each connected component of the complement is a cell, or equivalently, such graph could be represented as a ribbon graph, a graph glued from ribbons. So we enumerate graphs with a given number of vertices and with a given number of with a given valences of these vertices, and G is the genus of the ambient surface, and it could be computed from the number of edges and the number of faces by Riemann-Hurwitz, by the Euler characteristic. So the numbers that we are interested in is just the number of graphs embedded to a given surface of a given genus with a given number of vertices and given valences of these vertices. And as it usually happens in combinatorics, graphs, all the objects are counted together with the taking into account their automorphisms. Another example of such a series.
So the maps are just the ways to embed the graph.
Yeah, up to isomorphism. Another situation is just Hurwitz numbers of the previous talk. These are meromorphic functions, which has which is considered as a ramified covering over projective line. The preimages of infinity that are poles have prescribed order of ramifications, so we prescribe the order of poles, and besides there are some number of m of simple ramifications which are just Morse critical points, and we enumerate all possible such coverings up to also natural equivalence with a given ramification data. So the number of ramification points is related to the genus of the covering surface by the Riemann-Hurwitz formula. So it's we can fix either M or G. And again, so we count the number of such functions.
And what is M?
M is the number of poles. M
No.
is the number of poles, the number of pro-images of infinity. And the degree of the covering is sum of ki's. And these two examples can be included to a large family of functions, which I write here, and I call it a hypergeometric family of solutions to KP hierarchy or Orlov-Sherbin tau function. It's given by explicit formula by summation over Young diagrams. There are some contributions corresponding to Schur functions in P variables and also Q variables, and also some factor in front, which is called content product. And these are this is an infinite series which I consider as a function P1, Pm, P1, P2, and so on. And there are some extra coordinates or parameters that I treat just as parameters. So Qis are parameters which are collected in the series called Y, and also there is a parameter Ci which enter the series Psi which appear in this content product. So there is combinatorial rule how to construct such a factor from the given function Psi. So this is an explicit formula, and this is called this is just what I consider, and this is known to be tau function of KP hierarchy. So this is just the beginning. So as I say Pi's are just the coordinates, and Ci's, Qi's are just additional parameters that could be specialized. And Hurwitz numbers and enumeration of maps correspond to a certain specializations of these functions. So, for instance, the case of Hurwitz numbers corresponds to psi equal to y, the first line, and the case of maps corresponds to specialization exponent of psi is equal to 1 plus y. So this is just different cases. But there are also many other specializations which corresponds to some other kinds of Hurwitz numbers studied in the literature. And these I include so-called monotone Hurwitz numbers, strictly monotone Buscemi-Schaffer numbers, hypermaps, and so on. So all known types of Hurwitz maps studied in the literature are some specializations of this function. And also there is information about Q variables which are hidden in the function y. They correspond, in the language of Hurwitz numbers, they correspond to additional type of ramification over the origin rather than infinity. So if we have no special attention to the ramification over the origin, we just put y equal to z. So there is a huge literature on this particular function. So in spite of this part that it is just a single function, there is a huge literature. And this is just, I just show you some small piece of the literature on the subject. These are dozens and dozens of papers. And they interested this function by several reasons. One of them is that they really appear in some applications in combinatorics and mathematical physics as in the theory of matrix models, and even in some cases of in some special cases of Gropen-Witten theory. But mostly, the main reason to consider this function is that it happens to be governed by the topological recursion that I'm going to speak about. And this is, on one hand, quite easy to study because there are explicit formulas and there are many, many nice combinatorial ways to study this function. And on the other hand, this exhibits all the nice properties of topological recursion. So this is a kind of most simple, but on the other hand, rather advanced models where the topological recursion works. Okay, so what is topological recursion about? The idea is just use not the original potential, but what I call an point correlator function. So this function depends on x1, xn. The number of variables is different for different n. So we have some family of such a family of functions for different g and n. And this is an infinite series, and we wish to compute it in a closed form. But what does it mean to compute a series in a closed form? So it happens that in many cases, one can apply certain change of variables such that in the u variables, this function becomes rational, just rational. If a function is rational, then it is governed by a finite number of coefficients, and it could be given in a closed form.
Is it just assumption about
This is just how to say the leading idea. So we wish to find such a change. Yeah. So let me just show how it works in the cases of enumeration of maps and Hurwitz numbers. For the case of enumeration of maps, this change is just like that. So we change each of the variables xi, we replace by zi divided by 1 plus zi squared. Then, for instance, for gn equal to 0, 3, this is in the original x variables, this is an infinite series in x1, x2, and x3. But in z coordinates, it takes such a simple form. So it computes all Hurwitz numbers, all these numbers of maps with of genus 0 with 3 vertices in a single closed formula. For the case of Hurwitz numbers, the change is slightly more complicated. It's not algebraic. It contains an exponential, but still, when you apply such a change, the 0,3 function takes such a simple rational form. So the idea is to find such a miraculous change of variables such that the function becomes rational. So in the general case for our family of functions of hypergeometric type, there are two sets of variables which are encoded in the two series y and psi. And if these series are specialized in such a way that these are polynomials, then the corresponding change of variables is represented here. So the change is not so obvious, but however it works. So it's a formal series in Z. In the neighborhood, it's an invertible series. So we apply such a change of coordinates, and by the way, this change, we have a single change for all possible G and M. And after this change, the corresponding endpoint function becomes rational. This change was suggested, and the statement was proved in the paper by Alexandrov, Chapuis, Renard, and Harnat. And the proof was rather complicated, and the polynomiality was essential in this proof. So what we suggest in our approach, we say that the same change works actually in much more general context, and we provide a new tool which provides a simple answer when all this kind of formalism does work. So let me now explain what is the idea of topological recursion. So the idea is topological recursion. So the goal, as I said, is to compute HGN in the closed form. So we have a change of coordinates, and we expect that HGN become rational in these new coordinates. Rational, it means that it is a ratio of two polynomials. And moreover, there is an explicit description what could appear in the denominator, what are poles of this rational function. So we take our series x of z and extend it as a global function. So now the convergency is essential because we consider x of z as a global function in the variable z. It has some number of critical points, which I denote a1, an, and these are the only points where the poles are allowed. So the function HGN written in z coordinates only has poles at the prescribed positions for each of the variables. So these are a1, an. And moreover, there are some so-called loop equations which describe the principal parts of these poles. So we have a global rational function. We have identified the principal parts of its poles. And then we know that if we know the principal part, then the rational function is uniquely determined by the principal parts of its pole. And this is how we find the function. So this is a really amazing procedure. The induction of topological recursion uses the study of the functions as the poles. And these poles are, so we really use the convergency of our series, consider an analytic extension of this HGN in z coordinates. And this, we study the function at the points of poles. And these poles are, of course, beyond the convergency radius of this series. So we study global properties of this function, the global behavior of the poles, to identify poles which are far from the origin where we expand the function. And as long as the function is computed, then we re-expand it at the origin in the original x coordinates, and the Taylor coefficients of this expansion are the corresponding quantities that we can compute. Yeah, so the rationality and the convergency is really an essential ingredient of this procedure. Otherwise, the topological recursion is not even formulated. So to be more concrete, now I pass to the details. So instead of, to be correct, to be honest, instead of n-pom functions themselves, one usually uses in this inductive procedure what's called Kroeter differentials, which are just a different way to pack the same numbers into geometric series. And instead of monomial xi to the power ki, we take just the differential of this monomial. So this is a differential with respect to each of the variable x1, xn. And also, by some technical reason, there is a singular correction of 0 to Kroeter differential. which involves a pole on the diagonal. This is just experience shows that without this correction, the formulas become more complicated.
Is there a differential in x side?
If you,
Di small.
yeah, the differential considered just as a function in the ice variable.
This correction term, does it arise in, let's say, all applications of
The formulas that I will write later could be written if you, they become more compact if you apply this correction. And so the topological recursion allows one to recover the whole all correlator differentials or all correlator functions from the initial data. So what are the initial data? So we have a projective line with the global affine coordinate z, and also a function x on this line. And we are interested especially in the critical points of this function x. It's better to assume that x itself is rational, but sometimes we relax this and we just assume that the form dx over x is rational. So x itself would contain, for instance, exponentials. So the assumption on this function x is that the form dx over x, defined originally as a power series at the origin, extends as a global rational differential one form on the spectral curve on CP1, and all zeros of this form are simple, and we will study all the functions in the neighborhoods of these poles, of these critical points. Then besides we have one-point differential and two-point differential. So these are just initial data of our spectral curve. The 0-1 differential is just a differential in one variable, and there is some condition on the behavior of this 0-1 differential at the critical points of dx over x, or critical points of x. And 0-2 differential is given by an explicit formula. It has in z coordinates such a simple form, and it has a pole on the diagonal. And then the whole procedure, these are initial data which allow one to recover all differentials by the following way. So this topological recursion uses following ideas or principles. So first we compute omega gn from the following conditions. The first condition is that it should be rational. For the exception of 0-1 and 0-2 cases, all other differentials should be rational with respect to the global differential on the spectral curve with respect to each of the variables. And all the poles allowed are only at the critical points of x, and the requirement that there is no other critical points, no other poles. And also there are some conditions which identify the poles. And these are two conditions. We take our differential and we require that the principal part of the pole belongs to certain space that I denote by dxi. So dxi, so xi itself is a certain space of functions defined in the neighborhood of the poles and is spanned by the functions of this form. So what's written here? We have a differential operator x over dx, And since dx has a simple 0 at AI, this differential operator, this is a vector field, it has a pole at each of AI. And each time when you apply this operator, the order of pole increases. So when we apply this operator repeatedly many times to a function which is regular at AI, we obtain functions with the poles of bigger and bigger order. One can see easily that the space spent by these functions is somehow has half dimension in the infinite dimensional space of all principal parts. So, for instance, the order of pole of such a function is always odd. So the functions of this sort span certain space of functions, and we say that omega gn should be locally represented as a differential of functions from the space xi. And second relation, which is called quadratic loop equation, says that if you take certain combination of this omega gn, then they also belong to the same space of differential forms that I denote by dxi. So both conditions are local. We impose certain condition on the Laurent expansion of omega gn at the points AI. And it proves out that these two conditions are determine the principal part of omega gn uniquely. And therefore, by induction, we can recover omega gn by induction gn. So this recovering procedure expressing omega gn in terms of the principal parts of the poles could be written as a closed residual formula as a certain combination of some residues. And this complicated formula is usually presented in all texts on topological recursion, but I avoid this formula because the very reason, the very origin of this procedure is here. So what we use in practice is just these properties: rationality, projection property, and loop equations. So for the case of generalized Fourier numbers for our geometric series of hypergeometric type, so I recall that it's a series. These are numbers which depend on parameters, and parameters are collected into two series psi and y. The corresponding change of coordinates is written here, and we impose certain analytic assumptions so that x of z should be global function. But anyway, the 0,1 and 0,2 differentials, even without analyticity assumption, just take this form in z coordinates. So y is just the same y that was written here, and the z and x are related by this relation. So we use these 0,1 and 0,2 correlator differentials as initial data of topological recursion, and we would like to understand whether, if we start the procedure of topological recursion, do we recover the omega gn or not? So once again, the initial data of our topological recursion are written here. So spectral curve is a projective line with a affine coordinate z. X function is given by this mysterious change of coordinates. And 0, 1 and 0, 2 created differentials also expressed in terms of initial data. And then we start the procedure of topological recursion. Then the main theorem claims that if we apply this data and also if we impose certain analyticity assumptions that dx over x is rational and also critical points are simple, then it proves out the following thing, that these corresponding omega gn associated with these generalized Hurwitz numbers satisfy a rational, they satisfy rationality property, and also the loop equations are also automatically satisfied. But sometimes it proves out that for certain choices of initial parameters, the corresponding omega gn attain an extra unwanted poles, and so the whole topological recursion is not necessarily satisfied. So this situation in the literature is known as a blob topological recursion. So the local condition on the behavior of omega gn at the expected critical point, at the expected poles is satisfied, but probably there are some extra unwanted poles. And there are also some cases where they do not appear. I will say in a minute. So this theorem is a byproduct of a certain formula that we derived, explicit formula for an endpoint function. I will not represent this formula, but I will just explain how it looks like. So we have initial data collected into genetic series psi and y, and this formula involves derivatives of these functions psi and y, and we take certain combination of derivatives and also apply some several times the operator di, which increases the order of pole. And the very structure of this formula implies that the corresponding function belong to our space that I denote by xi. So the local structure of the principal part of the poles is implied by the very structure of this formula. So let me just show a couple of examples how this looks like. So 0,3 function, you see, it involves derivatives of psi, and 1,1 involves also derivative of y. So in a sense, this provides already a closed formula, even without analyticity assumptions. But however, if psi and y are rational, for example, then this function becomes also rational. Okay, so as I said, the topological recursion is not necessarily, unfortunately, valid in full generality, but there is a way to correct this problem. Namely, we involve also parameter h bar to the initial data. So let's assume that the initial data, the C and Q parameters, are infinite power series in h squared. Then all our closed formulas are also valid in almost the same form. And this theorem is also valid. So the validity of loop equations is implied by the very structure of this closed formula. So we conclude that for any h bar deformations of the initial data, we have just the same initial data, the zero correlators do not change. We have the same initial data of the spectral curve, and linear loop equations and rationalities are still satisfied. So the question is it possible to choose such a H-bar deformation that the unwanted poles are cancelled? And so the claim is that we try to find such a H-bar deformations, and that there are some cases where we observe such deformations, and these are some special cases. So you see, in first two lines, these are some cases. The first line somehow generalizes the case of enumeration of Hurwitz numbers. The second line generalizes the enumeration of maps. And these are the cases where H-bar deformation is not needed. But also there are certain cases which correspond to so-called R-spin Hurwitz numbers, or to certain Guri-Waffa potential corresponding to home-fly polynomials of toric knots, where the H-bar deformations are essential. So in the initial table, here, depending on the situation, sometimes we need to apply a suitable H-bar deformation for the topological recursion to be satisfied. So let me conclude that this mysterious loop equation, which usually is proved by some advanced combinatorics, appear to be just a simple byproduct of our explicit formula, and somehow is obtained automatically. But what is in opposite, what is the most delicate and the most complicated from the technical point of view is just the property that the unwanted poles are cancelled. So we automatically obtain that the corresponding endpoint functions are rational, but the study of unwanted poles is just what's is subject to the study. Thank you.
Let's complete questions. Are there any questions in the audience? Are there questions in Zoom? Okay. I also have no remark except for request to send me file.
Денис contains. Если я послал вам файл, его можно расширить потом.
So let's send it again. We have 7 minutes.
Почему-то никогда не был никогда. Я вроде бы успевал, да?
Знаете, я никогда вас не видел. Ой, привет. Спасибо большое. Все, большое спасибо. Уже нормально сказать. Ну, ты знаешь, я вчера понял. Хорошо, может, без конференции. Там правая часть состоит
to WDV and related space.
Right. Thank you very much to the organizers for inviting me. It's my honor it's an honor for me to give a talk at this workshop dedicated to the memory of Boris Anatольevich Dubrovin. And what I'd like to discuss relies very directly on his fundamental works in the area of Frobenius manifolds. And this is joint work with my PhD student Mali Al-Kadem, so it's partly available in this reference, but some things are in preparation, which I also would like to discuss. So I'd like to review some solutions of WDV equations of two types. So first I'm going to review rational solutions, and then the main topic is the trigonometric solutions. And in the last part, I'd like to discuss something general about WDV equations and slightly different equations. Some kind of relation between two sets of equations. So we came across this from studying of trigonometric solutions, but actually it's not dependent on the type of solutions. It's just some relation between the equations as such. Right. Okay. So let's maybe start with the rational solutions, and this is goes back to the very famous example of Frobenius manifold on the orbit space of a Coxeter group. So this was introduced by Dubrovin in the early 90s, and it's available in his lecture notes, which are published as a book, and and sometimes this is referred to as the Bible, so meaning the Bible of Frobenius manifolds, at least. Right. So, but parts of the structure was available was discovered earlier by Saito, but Saito did not consider prepotentials, for example, as far as I understand, and this is key example where potential is polynomials, and actually these are all such examples as Alexei Gusalaev was discussing as well. So anyway, let's consider n-dimensional vector space with a standard bilinear form, and let's take a root system in this vector space, and let's consider Coxeter group generated by orthogonal reflections with regard to this root vectors, so the corresponding hyperplanes. So this is a finite Coxeter group. Then this orbit space is a Frobenius manifold, but I'm more interested in the so-called almost dual Frobenius manifold introduced by Boris Dubrovin a bit later. And let me just mention that the multiplication for the almost dual almost Frobenius manifold is given by this formula where circ is the kind of standard Frobenius multiplication on the orbit space, and E is Euler vector field, and that's like inverse operation to the multiplication by the Euler vector field. But we don't need this circ, we really need this star product, which I'll talk more about later. And the prepotential for this star product.
The scalar product is the same?
No, not the same. So here we have the invariant bilinear form for the Coxeter group in linear and dimensional space, while on the orbit space the main product is the cytometric, which is the lead derivative of this bilinear form with regard to the identity field. So I don't really need this cytometric on the orbit space. It's just the standard CN, where the group acts bilinear transformations, and we take invariant bilinear form for the Coxeter group. Okay.
No, I mean the metric on the dual, almost dual Frobenius manifold.
That's
the metric.
Yeah, that's the metric. So that's what I mean. So the metric, it's just n-dimensional space. The metric is constant, of course, and that's just the invariant bilinear form, invariant scalar product. So the group acts by orthogonal transformations with regard to this metric. And this is the Frobenius metric, yes. So there is a Frobenius algebra with this kind of multiplication, and that's the metric which is constant at every part of the CN. It's constant, and it's the Frobenius metric for this multiplication. So now the prepotential has very simple form. So it's just sum over root system alpha x square logarithm alpha x, where x is our element of the vector space, and it's not a Frobenius manifold just because the identity field is not constant in the flat coordinates of this form. So just standard coordinates x1 xn. Namely, identity field is this Euler field, sum of xi d by dxi. But otherwise, various axioms are satisfied. So that's called by Boris Dubrovin almost Frobenius manifold. Okay, so now, yes. So rational solutions more generally have this form. So let's start with a collection of covectors A in a vector space. And let's consider sort of similar expression as for the root system, but it's more convenient to work with covectors. It's similar expression as if A was a root system, but now A is an arbitrary set of covectors at the moment. And let's let's wonder when such a collection of covectors satisfies Witten-Digraph the Berlin equations, which I write here in a generalized form. So Fi is the matrix of third order derivatives, where one of the derivatives is with regard to variable xi. So namely, Fi is the n by n matrix if we have n-dimensional vector space whose PQ entry is this third derivative d3 over df over dxi dxp dxq. And here in the middle we have inverse of such a matrix, and otherwise we swap these two indices Fi of k. So that's a product of three matrices of that form, but in the middle there is a inverse of the corresponding matrix Fj. So the condition is that we can sort of swap I and k to get this equality. And let's assume this holds for all indices I, j, and k. So in Frobenius manifold, usually this is fixed to be of a particular form, but actually to be a particular linear combination. So like usually there is some b, which is one of the derivatives or a linear combination of such a derivatives, Fi, and then that plays the role of the metric, and then we take inverse. But actually it's equivalent to impose all these conditions or just to fix a particular linear combination. And I will get back to this later on. And in such form, it appears in the work of Morshakov, Mironov, Mirozov, such form of WDV equations on Zeiberg-Witten theory. So these are equations I'm interested in, but just because there is no distinguished direction. So it's kind of a bit more natural to set this like that, where all the indices are on equal footing. But it's not very important because of this equivalence, actually. So it's just for convenience. So these are the equations. Now let's associate with such a collection of covectors some bilinear form on the vector space. So just sum of alpha x, alpha y, and let's assume it's non-degenerate. So in particular, these vectors have to generate our vector space. And then we can identify vector space with its dual. Under this identification, that's standard way to identify it. And then covector alpha corresponds to vector alpha denoted by alpha check. So I'd like to recall now the definition of Sasha Veselov, who initiated like general study of such solutions of WDV equations. And for that, we need the notion of check system. So the collection A is called the check system. If for any,
You say check?
yes,
Check.
check for this sign check.
Sorry.
But we may also say V, and then it's Veselov system for simplicity. Right. So then for any, let's fix some two-dimensional plane in our vector space, and then for any, and let's take alpha in such a two-dimensional space, subspace. Then we sum up over beta from this two-dimensional space, sum up covectors from our set. So beta is in this intersection, and then we take a combination of this covector beta with certain coefficient beta calculated, evaluated at alpha check. So this is a sum of covectors, and the requirement is that it is proportional to the covector alpha for some coefficient of proportionality, which may depend on the plane which we start with, as well as on this vector alpha. So that's some kind of property. Equivalently, one may think of this as yes, for any yeah, thank you, for any pi and for any alpha. Thank you. Yes. So it's not trivial only if pi contains at least two vectors from our collection. So actually we talk about finitely many planes, but we have to consider all of them. Thank you. And the equivalent condition is that certain bilinear forms are proportional. So GA is one of them, and one can similarly define JP by summation over covectors from two-dimensional plane P. Then these two bilinear forms are proportional, provided that there are at least three covectors inside this plane. And if there are only two covectors, then they have to be orthogonal. That's another way to think about these conditions. Sorry? That's right. Thank you. GA, yes. Yes, with respect to GA. Right. So root systems of a Coxeter group is an example of such a situation. So R is a check system. There are some more examples here. So this is kind of type A n example, but then there are coefficients Ci, Cj. So it depends on n+1 parameters, I suppose. So you see, if we rescale the vectors, this notion is sensitive to such rescaling. So it's important that coefficients have precisely this form, and one cannot have, for example, arbitrary coefficients here. And actually, this example, I think, appeared in the talk of Sasha Varchenko in some one-dimensional case, which he mentioned as an example.
It looks more like just one half of the system.
That's right. So yeah, you're right. Yeah, I mean, it's not too important. So we can in this kind of rational situation, we can replace proportional vectors with a single vector by adjusting some kind of coefficient in front of them. So this notion of check system is not very kind of sensitive to this. So one can always get rid of proportional vectors. So yeah, for some convenience, it's just positive half of the root system here, and this can be assumed more generally. There is type B family here as well. Yeah, and the statement is that actually it's equivalent that such a function satisfies WDV equation. It's if and only if A is a check system. But of course, it's not quite clear what this collections are, but there is this nice linear algebraic reformulation of this property. Now, so it is standard if we have a Frobenius sort of WDV equation, so there is a corresponding associative product, which is one can also restate WDV equations as associativity condition, and in this case it has the following form. So we take a complement to our hyperplanes where covectors vanish. That's MA. So let's take point X, generic point on such a no, X is just any point outside of our collection of hyperplanes. We take vectors attached to this point, and then multiplication has this form. So it's U star V. This is some coefficient which depends on our position X. And otherwise, we have these vectors alpha check, and we sum up with this coefficient. So that's covector alpha evaluated at U and at V. So actually, so these properties which we talk about, WDV equation, so check system is equivalent to associativity of this multiplication, or another way to rephrase it, again, it's reasonably standard as a flatness of some connection, and this connection has this form in this situation. I won't need it later, but it's possible. Right. So this is kind of the basics, and then there are two operations which one can perform with check systems, preserving the class of check systems, and they are very natural. So one is to take subsystems, and another is to take restrictions. So let's see how this works. So to take subsystems, we do the following. So we take a linear subspace in our vector space V star, and we take those covectors from our system which belong to this subspace. So let's call this beta. So let's also assume that they span this subspace. In other words, we take some of our covectors and we span a vector space by those covectors. This is a subsystem beta B. And we can think of this as covectors on W check inside the vector space. And
What's the difference between check and star?
yeah, so check was a vector corresponding to our covector under the ID.
W check.
Yeah, so W is in the dual space, and W check is the corresponding vector space in the vector space. So we identify. No. So can I write? So we identify a vector space with the dual space with the help of this bilinear form, and then alpha is here, and alpha check is the corresponding vector there, and this is the same just for the subspaces. So anyway, so if we take such a subsystem, then it's also a check system under some kind of genericity assumption. And another operation is taking restrictions. So it's in some sense it's sort of dual operation. So for a subsystem B, we take corresponding hyperplanes beta x equals 0, and we intersect all of them. This is the subspace WB. So it's intersection of some of the mirrors of our configuration. And then we restrict all the covectors which are not 0 on this subspace to this subspace. So this is a collection of covectors pi BA. And then the restriction is a check system. Again, and some sort of non-degeneracy assumption is needed for that. So in this case, we take intersection of mirrors, and we restrict all the covectors to this linear subspace. Or if you think in terms of inner product, you make orthogonal projection to such a subspace. And this again gives a check system. So for root systems, for example, subsystems of a root system is always a root system, so it's not very kind of interesting maybe, but restrictions of root systems are not in general root systems. So this gives new type, I mean, additional check systems. And there is this kind of duality on which I mentioned of Dubrovin, and a version of this duality holds for this kind of restrictions. In this case, one talks about discriminant strata. So if we go now to the orbit space, then we have discriminant strata there. One can restrict Frobenius multiplication to this strata, and there is such a duality relation. It remains to be satisfied. So these projections, they are essentially about like in terms of orbit space, we go to the discriminant strata and consider all the structures there. Now let me discuss. So this is the geometrical meaning of these restrictions in terms of orbit space. This is after the projection to the orbit space, these subspaces become strata in the discriminant. So now let's discuss trigonometric solutions. So here they have this structure. So it's some of the again, we have a collection of covectors A, but now we also have some constant C alpha attached to each covector alpha. That's the ingredient. And then the key part of the prepotential is going to be this form, is this sum C alpha f of alpha x, where f is some kind of special function. It's a trilogarithm function, which has the property that its third order derivative is cotangent z. So this is actually analogous. I have it on the slide later, but this is an analogous function to the function z square log z in the rational case, which we dealt with before. So this function has third derivative 2 over z, and this is just trigonometric analog of such a function from the rational case. So that's why we have cotangent z. That's trigonometric analog of the function 1 over z. Coefficient 2 is not important. So that's natural generalization of that class, but also by some reason one adds additional cubic term here, which depends on additional single variable y. So it's some polynomial part. So it's kind of a function of n plus 1 variables, and x variables and 1 y variables. So such solutions were considered by Jovinarz and Martini for root systems. They also appeared in 5-dimensional Seiberg-Witten theory. And in terms of almost duality, they are expected to be almost dual solutions for the Frobenius manifold structure on the orbit space of extended affine Weyl group. So such Frobenius manifold was introduced by Dubrovin and Zhang, and studied further, in particular by Dubrovin, Stron, Zhang, Zhou, most recently by Brini and Van Gemst, and this almost duality statement is confirmed in type A in this paper by Riley and Stron. Now, also these solutions appear as in the context of quantum cohomology, namely one takes simple singularity, simple isolated singularity of ADE type, one consider its resolution, and one looks at the equivariant with regard to cis direction of quantum cohomology of the involution. So we can say small cohomology, but it's not too important because the non-trivial classes are two-dimensional as well as zero-dimensional. But you can think of small quantum cohomologies, and that's precisely the so quantum multiplication are precisely governed by such type of prepotential. So this was the work of Brian and Galampour. And then there are many parameter deformations of classical root systems appearing in the work of Maxim Pavlov on reductions of Yegorov hydrodynamic chains. I started to consider the solutions for any configuration a while ago. Now let me give some more settings. So let A be in general finite set of covectors. We have to assume additionally that it belongs to a lattice of rank n. I mean, let's assume that. There is a version of this standard form GA where that's as before, but now we have this coefficient C alpha, some coefficient C alpha in front. So alpha check is defined similarly to the rational case. And then there is this notion of some kind of notion of strings or series, which is similar to what happens for root systems, but let me define it in this context. So let's consider for each covector we take all the covectors proportional to it. We are not interested in this set of covectors, and we distribute all other covectors except those proportional to alpha into some collection of disjoint series, gamma alpha s over union over s. And the property is that if we take two vectors from this set for fixed s, then either their sum or their difference is an integer multiple of alpha. So this is the key condition, and there is some also maximality assumption, so we don't have too many series. So let me demonstrate how it looks for BC2 root system. So that's BC2 root system containing these vectors, and then for alpha equal E1 we take E2, E1 plus E2, E1 minus E2, because these are different by E1, and if we say instead of E1 minus E2, we can equivalently think of E2 minus E1, and then again, all these three vectors, E2 minus E1, E2, E1 plus E2, they are different by E1. So it's important that the difference is between any two of them is integer multiple of E1. So they belong to, these three vectors belong to the single series. By definition, we are not interested in the proportional vector, and this 2E2 is in the remaining series. So that's the condition. If we take instead of E1, 2E1, again, we have to have this series decomposition. And what happens is that this series from, so that's actually written here. So what happens is that this series from before, E2, E1 plus E2, E1 minus E2, it splits into two series. Here, because this difference between these two vectors is just 1 times E1, but now we can see the series with regard to 2E1. So these two vectors are no longer in one series, but this one and this one, E1 plus and minus E2, they are still in the series of 2E1, because the difference is exactly 2E1. But this one, E2, now forms a single series as well as 2E2. And so on. And the condition is that this holds, so we do this decomposition for each alpha. And then check system in this case is defined somewhat similarly to the condition in the rational case, but the summation now is over each alpha series. So for each alpha series, for each S, we have to have such type of proportionality that
is gamma what you were calling B before? Is gamma the same as what we called B?
Did I have B?
It's the same thing as B.
Where is B?
B, which is the generates.
No, it's not. I'll have an analog of this subspace in a moment. No, at the moment it's not really that. So gamma is kind of discrete, so it's not a vector space. It's just a subset of vectors of our configuration arranged in a certain way. So just certain subsets. So it's finite.
I was trying to check if I was following, and I apparently proved that I'm not. So it's complicated.
Sorry. No, I mean that's examples of such collections. So if A is a trigonometric check system, then this rescaled version of the covectors is a rational check system. No, I mean, so let me tell you slightly better. So we fix alpha. Then let's imagine that our all covectors are on the upper side of the half plane for simplicity, and then we, if some of them are different by an integer multiple of alpha, say 2 alpha here and alpha here, then we take them into one alpha series. And then we continue. So there is just one here, so we take it into the second alpha series. If there is another one different by integer multiple of alpha from this one, then we'll join it to the same alpha series as well, and so on. So this way we sort of exhaust, we decompose our collection into union of subsets. That's the idea anyway. Okay. Right. So now, so if we have a trigonometric check system, then we have a rational one as well by this simple process. But this class is more restrictive, so let's wonder about. Let's discuss WDV equations. So let's be now more precise about this cubic term. So it's this additional variable y, so which corresponds to the one-dimensional space U. So we have y cubed and y times some standard quadratic expression in x variables in terms of our multiplicities C alpha. And then we have this term with this polylogarithm function whose third derivative is cotangent C alpha coefficients there, and let's allow also parameter lambda in front, which I, for convenience, rescale to 2 lambda. So that's the ansatz for the solutions, which seems to be right one in a sense, and y plays a special role. So let's also denote it x n plus 1, and analog of Euler vector field will be d by dx n plus 1, and WDV equations are standard as before. Just for convenience, we can fix now n plus 1 here because there is a distinguished direction. But equivalently, we could just think about previous WDV equations. So such solutions exist for any root system and invariant under the Weil group multiplicity function C alpha. So for suitable alpha, this gives a solution. And the corresponding associative product has this form. So that's kind of, this part is similar, somewhat similar to the rational case. It's just instead of 1 over alpha, we have cotangent, but also this Euler field, I mean, d by dx n plus 1 vector appears there, and this vector is actually unity of this associative product. So, and then there is a way to relate WDV condition to this language of check systems. So here we need 2 more bilinear forms on the space lambda 2v. So they are just kind of defined by some direct formulas, where z and w are elements of the exterior square of our vector space. So we have this sort of formulas. A plus has to be defined, but let me maybe not go into details here, but essentially it's half of root system, half of collection A, but some vectors have to be changed to the opposite ones. And the difference is that here we have this bilinear form GA, which we defined before, but there we don't. And then under some, again, this technical assumption, WDV equations are equivalent to 2 properties. Firstly, A is a trigonometric check system, but secondly, we need this extra condition, which is not appearing in the rational case. So these 2 bilinear forms are proportional, and lambda is essentially coefficient of proportionality of these 2 bilinear forms. And this is equivalent to WDV equations. So the converse is also true. So in the root system case, these 2 bilinear forms are actually invariant under the action of the Coxeter group. So therefore, this proportionality is kind of automatic because it's a bilinear. These 2 forms are invariant bilinear forms on an irreducible representation lambda 2v of the Coxeter group, so they have to be proportional. And this plays a role of kind of Coxeter number for the lambda 2v instead of the usual Coxeter number, which may be thought of as something related to the reflection representation. Right. So and then there are analogs of this restriction operations and taking subsystems in the rational case. So the subsystem of a trigonometric check system is a trigonometric check system, and restriction of a solution of WDVV equation under some assumption is also a solution of WDVV equation of similar form, but on this smaller dimensional space. So there are some kind of analogs of the statements in the rational case, but there are differences. So here we talk about trigonometric check systems, and here we talk about solutions of WDVV equations. Right, and now in the last few minutes, I'd like to discuss some general. It's not kind of related to what I've not much related anyway to what I talked before. So there's some general relation between WDVV and commutativity, so-called commutativity equations, which I actually find very surprising. So let me try to discuss this. So let's consider function f just of say n variables, so n plus 1 variables as we had before, but it's at the moment it's arbitrary. It's not a particular rational or trigonometric form. Just let's think of any function. Then, so I mentioned in the beginning that the WDV equations in this form fi of j inverse fk is equal to this way around, other way around when we swap k and a. So this kind of WDV equations or generalized WDV equations, they are equivalent to the conditions here where we fix particular linear combination, and it's not difficult to see by some algebraic manipulations. And in the Frobenius manifold case, we have a distinguished direction T1, which corresponds to the unity which is flat, and that's constant. For almost dual Frobenius manifolds, we have this kind of Euler field, which gives actually constant metric constant expression sum of xi fi. So this was the case for rational solutions. In fact, if you check this, it's easier to see this combination is constant. And for almost dual, I find there was a distinguished direction of n plus 1, which gives a suitable combination, which is constant. But now it appears to be it's sort of kind of rather general property. So namely, let's consider the following version of equations. I don't quite want to call them WDV, although they are very close, and I think sometimes they are called WDV equations. So we have the usual third order derivatives here and there, and some I don't know, metric or some kind of coefficients g alpha beta in between, and then we swap the two indices. K goes to the right and L goes to the left, so we swap K and L as usual, but at the moment this G is not related to the F at all, so it's just some constant matrix. And then on the generosity assumptions, the statement is that there exists a linear combination E, sum of bi di, such that if we apply this linear combination to fijk, so by definition that's just this combination of third order derivatives, then we get actually this metric with lower indices. So in other words, if we take this special particular combination bi fi of third order derivatives, then what appears here in the equations is the inverse of that. So we don't assume in the beginning any relation of these coefficients with the third order derivatives of the prepotential, just some constant matrix here, as it happens for the usual WDV equation. So just some constant matrix, and then the statement is that actually this matrix is inverse to this combination, or to some combination of third order derivatives. So it's not very surprising that this combination is unique, but I think it's unexpected, at least for me, that there is such a combination. So, for example, I mentioned commutativity equation. So that's just the case of that when this G is identity. So G alpha beta is delta function, delta alpha beta. So then we start with the commutativity equation, and the claim is that generalized WDV equations like the one which I discussed, they follow just from that. but the structure is really different of this equation, but this seems to imply that. So appear to imply that. So there are some assumptions necessary of sort of non-degeneracy of flavors. So some kind of matrix has to have full rank, n by n plus 1 matrix has rank. If it's n minus 1 by n matrix has rank n minus 1. Some kind of assumptions like that in this case, and some non-vanish, some derivatives being not identically zero. And these commutativity equations, they actually appear in supersymmetric mechanics a while ago. And they play a role there, so they are useful for construction some supersymmetric mechanical systems. So example, just to conclude, so the last slide is the example of such a field. So this function f here, it is f is as before trilogarithm as in the trigonometric solution. So we have this function with some coefficients r, s, and k. So you could think of this as something related to BCN root system. Then one has to assume relation between these three parameters. So they are not arbitrary. So two of them define the third one. Then this function satisfies commutativity equations and actually also WDV equations. And this combination, in this case, it's not too complicated. So it's sine of 2xi, which has to be taken, multiplied by the corresponding third order derivative. And there is a certain function h in front. So this is what gives standard metric delta as we consider linear combination of third order derivatives. So that's an example of such a linear combination for commutativity equation for this particular solution. So this combination depends on the solution, but it exists in general. So thank you very much for your attention.
Okay, please question. Let me just side question. What is supersymmetric?
Right. So yeah. So no. So you.
I understand that it can exist. Why?
No, I'm not really sure about like physical background, but I mean, mathematically, so say thinking of Cauchy-Moser system, so you sort of, which was mentioned, so you extend the usual Hamiltonian with a number of fermionic variables, and so here with n equal 4, which I mentioned, that's often like 4 times n fermionic variables, so I think which satisfy extra relation, and then you have like your bosonic part of the Hamiltonian is the standard one. There is also fermionic part, and this is this together. Then there are other kind of operators or elements or functions, if you like, depending on operators depending on bosonic and fermionic variables, and altogether they are assembled into some algebra, which is usually superalgebra, and that's why it's called supersymmetric. So there is some kind of superalgebra which contains the Hamiltonian as well as various other operators. But Hamiltonian is kind of standard bosonic one plus some fermionic terms.
When you say that, when you mention example of Frobenius manifold as a factor of Euclidean space, by at what extent is this general example?
Right. So yeah. So this is actually, yeah. So there is a, like, so Alexei Pusulayev mentioned this earlier in the week. So there is a general statement of Hertling. In particular, there are no other polynomial prepotentials under certain assumptions on degrees of homogeneity. So there are slight technical assumptions, but roughly these are all polynomial prepotentials. General polynomial, but there are non-polynomial solutions as well. But if you assume polynomiality, which is reasonably natural, and some kind of irreducibility maybe, so then that's general polynomial Frobenius manifold.
More questions? Yes. Then, thank you, Michelle. Again. We have break for 45 minutes, roughly 44 minutes. Oh, sorry. One hour. 1 hour 44 minutes.
Все нормально, уже началась трансляция. Хорошо, спасибо. Можно начинать? Окей. Let's continue our session. Next speaker is Oleg Glukov, Moscow State University, WDVV equation and the theory of submanifolds in pseudo-Euclidean spaces.
First of all, I would like to say that I knew Boris Dubrovin from my early student times, from second course at Novikov seminar, and he had a very big influence on my papers also, on all Novikov school and not only. And it's a huge loss for all of us, and for me in particular. So I will call about curved VDVV equations and geometry of submanifolds with potential of normals. Curved Witten de Graaf-Verlinde equations are some generalization of classical VDVV equations proposed in, as I know, in 2017. It was first paper about curved VDVV equations, and paper is ref D. Authors Kozyrev, et al. 5 authors. Of course, after papers of Witten and de Graaf-Verlinde and Verlinde, these equations arose in many different contexts, and in supersymmetric multidimensional mechanics, for example, in flat space, arise VDVV equations. And in this paper, they considered the same situation in curved space. And then this physical model gives the following conditions. I define the curved VDVV equations. These equations, first of all, we have some arbitrary pseudo-Riemannian metric, Gij, and some three-valent covariant tensor, totally symmetric on all indices. And two conditions. First condition, covariant derivative with respect to this metric covariant derivative is symmetric.
So covariant derivative is also a symmetric tensor with respect to all indices. And second condition, equal not zero, but Riemann curvature tensor. So these two conditions give us curved VDV equations. And I will talk about the following observations, that these equations, curved VDV equations, are also very natural reductions of the fundamental equations of theory of submanifolds, as it was for classic VDV equations. So I recall my paper of 2006, when I proved that VDV equations are natural reduction of the fundamental equations of the theory of submanifolds. I recall definition of Dubrovin-Novikov Frobenius manifolds, but I will use not all Dubrovin's conditions. So not all Dubrovin's conditions on Frobenius manifold. I will consider the following condition: n-dimensional manifold with some flat metric G. So first condition, G is flat metric. And on tangent spaces of this manifold, there is some operation, so that this operation on tangent vectors of tangent space is, this operation is commutative, associative, metric is invariant metric in this algebra, so Gx is equal Gx Z. So we have Frobenius structure. Here G is invariant metric with respect to this multiplication. And 5 condition, fifth condition. If we have commutative algebra with invariant scalar product, so we have some three-valent tensor symmetric. This tensor is symmetric due to the second condition and fourth condition. And fifth condition is that covariant derivatives of this metric, of this tensor, is also symmetric tensor with respect to all vector fields x, x, y, z, and w. Of course, if we have flat metric, we can consider flat coordinates of this metric, and in this coordinates, this condition is trivial. It means that we have that our tensor is third derivative with respect to flat coordinates. These conditions, all these conditions except of associativity will be satisfied, and the condition of associativity gives us the VDVV WDVV equation. I will write here. Where eta is our metric in flat coordinates. In flat coordinates, it's constant in some non-degenerate constant symmetric matrix, inverse to the covariant method. So locally, any solution of this equation define Dubrovin-Frobenius, in this sense, Dubrovin-Frobenius manifold satisfying all this on these conditions. And I proved that these equations are, in 2006, I proved that these conditions these equations are reductions of fundamental equations of a theory of submanifolds. We should consider the most simple case when we consider totally non-isotropic submanifold in pseudo-Euclidean space with some signature. N-dimensional submanifold. N-dimensional. And we consider that this submanifold is flat. So first fundamental form of this submanifold is flat. Second condition, that this submanifold is submanifold with flat normal bundle. It's the most simple conditions. So we consider that our connection flat and normal connection, tangent connection flat, and normal connection also flat. And we should consider also the case when dimension is equal codimension of this submanifold. If function f is a solution of WDVV equation, then we consider the following. First of all, what P signature. It's pseudo-Euclidean space, so it's not Euclidean. Euclidean. I denoted some signature. It doesn't matter. In flat coordinates of this submanifold, we can consider the second fundamental forms of the following form. We have connection is equal to dimension is equal to codimension. So we have in this case n-dimensional normal space, and we should have n second fundamental forms. So I will denote it by upper index. If we consider the second fundamental forms of this form, then if F is solution of the WDVV equation, then all fundamental equations of the theory of submanifolds, the Gauss equation, the Peterson-Maynard-Kadazza equations, Gauss, Peterson, Maynard, and Ricci equations are fulfilled. Moreover, in this case, it's very curious that in this case, for this first fundamental form and this second fundamental forms, sorry, I did not say that we should consider metric. We consider metric in normal space. Hij is equal n I n j is constant at ij. We should consider scalar product in normal grammar matrix in normal space, which is constant multiplied by first fundamental form. In this case, Peterson-Maynard-Kadazza are fulfilled, and Gauss equations are equivalent to the WDVV equations, and Ricci equations are equivalent to the WDVV equations. It's the case when Gauss and Ricci equations coincide. Very unexpected thing for me in any case. Moreover, if we consider another case of Dubrovin-Frobenius manifold, when we consider not flat coordinates of the metric, but if there are some coordinates such that the metric is equal to Hessian of some function, I considered this case, by the way, in 1998 in my papers. In this case, if we consider that metric of this type is flat and all these conditions are satisfied, then the condition that this metric is flat and the condition of associativity give us the following form of WDVV equations, where instead of metric SIR, we should write the metric. It's not constant. The same equations will be satisfied, but here not constant metric, but metric given by matrix inverse to the Hessian matrix. It's also integrable equation, of course. It has like pair and so on. It was investigated in earlier paper, and then these submanifolds also arose in some context in some papers. I call it Hessian Frobenius manifolds, and these equations, when we have metric in form of Hessian matrix, also some reductions of equations, fundamental equations of the theory of submanifolds. In this,
This F and that F.
no, different. Oh, no. In the same. F the same.
Because in the drawing formalism, this is partial to F. This one is partial derivative of the upper one with respect to the unity.
No, I don't consider the condition of unity and the quasi-homogeneous and no Euler fields. I consider also these conditions. No condition on the existence of unity here. I consider this metric, and if I will consider in this case coefficients of connection of this metric are third derivatives with lower indices. So we will, I will not obtain it here, but it's possible to prove that the condition of associativity for the corresponding structural constant and the condition that this metric is flat are equivalent to these equations. Function f is the same. And in this case also, it was proved by me, and I talked about it earlier, that these equations are reductions of the fundamental equations of the theory of submanifolds. In this case, we should consider submanifolds. Again, we consider flat submanifold with this metric, with this first fundamental form, and we consider second fundamental forms. Again, dimension of submanifold is equal to codimension. Again, we consider HAG is equal to constant on Gij. It's not constant metric in this case, and here second fundamental forms equal to and they are structure constants of this algebra. Yes, BKIJ are structural constants of Frobenius algebra with this non-degenerate, invariant non-degenerate bilinear form, associativity, commutativity.
You say structure constants, you define multiplication.
Yes, it's structural constants of our algebra.
Or multiplication.
Yeah, multiplication. Yes, multiplication is.
Тебе надо было там вместо ЦК написать S.
Yes, you are right. And then, So if we consider first fundamental form in this of this type and second fundamental forms of this type, then in this case, again, Gauss equations are equivalent, the Ricci equations and Peterson-Maynard gradation are fulfilled. And Gauss equations for submanifold equivalent to WDVV equations. So it's also reduction of the fundamental equations. And by Bonnet theorem or generalization of Bonnet theorem, if all fundamental equations of the theory of submanifolds are satisfied, then there exists some submanifolds with such first fundamental form and such second fundamental form. So it's exists. So we can realize Dubrovin-Frobenius manifold with constant metric and with Gaussian metric as some submanifold, n-dimensional submanifold in 2 n-dimensional pseudo-Euclidean space, such that multiplication is given by second fundamental forms, and scalar product in this algebra is given first fundamental form. So our algebraic Frobenius structure are realized as via fundamental forms of this submanifold. What about curved WDV equation? After these results, I introduced so-called submanifolds, the special class of submanifolds with potential of normals. I asked specialists in theory of submanifolds, they never considered this class. This class is the following. If our submanifold is given by some radius vector in pseudo-Euclidean space, of course, it's well known that basis in tangent space is given by derivatives of this radius. What? Sorry. Yeah. Sorry. Sorry. Of course, it's given by n parameter, vector of n parameters, which is x1 from u and so on, xm from u. N parameters. So here we have derivative with respect to ui, and x1 and so on, xm are pseudo-Euclidean coordinates in pseudo-Euclidean space. By the way, I did not say here that our signature should be also coordinated. So signature of our pseudo-Euclidean space should be coordinated with signatures of metric and metric in normal space, metric in tangent space and metric in normal space. It's simple condition. And we have some basis in normal space. Well, n minus n from u. And I will consider submanifolds with potential of normals. First of all, this is submanifold when dimension is equal to codimension, as in these examples. So we have, and it doesn't matter. So we have n-dimensional normal space and n-dimensional tangent space. And condition which I observed in my examples is the following. that there exists some vector function from U such that are partial derivatives of Ui. All the submanifolds which were constructed for Dubrovin-Frobenius manifold with constant metric and Gaussian metric necessarily have this condition. So in these realizations, there exists some vector function such that we can consider the basis in normal space in such form. This is some strict condition, really. But all these examples are of this form. So if we consider this condition, then it was proved by me that there is a very interesting geometry for such submanifolds. In this case, we have some duality between vectors R and N. If we consider, in this case, we can consider submanifold given by vector function N instead of vector function R. And in this case, Gauss equations for this submanifold are equivalent to the Ricci equations for this vector function, and vice versa. And the same to Ricci condition here is equivalent to Gauss conditions here, and Kadats equations are the same. In this case, we have second fundamental forms as a tensor for submanifolds with potential of normals. Second fundamental forms and second fundamental forms give us some three-valent tensor. Moreover, in this case, if we change these two vector functions, of course, we have the connection of metric here is connection in normal bundle here, and vice versa. Connection for metric here is connection in normal bundle here, and so on. Okay, if now I would like to introduce some non-flat Frobenius manifold. In this case, metric is arbitrary, not flat. Arbitrary metric. It's some pseudo-Riemannian n-dimensional pseudo-Riemannian manifold with some metric. We have some multiplication such that this multiplication is commutative. Condition 3. So condition 4 is the same. We have invariant scalar product. In this case, again, we have some three-variant tensor, which is symmetric with respect to all vector fields. And the condition 5 is also the same. We have 4-valiant symmetric tensor. It should be symmetric tensor. And condition 3, it's not associative algebra. It's generally speaking non-associative algebra, and this condition is the following. Here I will write some constant c because we can change sign here. So if we have some n-dimensional submanifold, n-dimensional manifold with such structure, it's not flat Frobenius manifold. We have some Frobenius algebra, non-associative Frobenius algebra. It's commutative with invariant Frobenius structure. And in this case, if we consider structure constant these conditions give exactly conditions for curved W dvv equation. So all these conditions are equivalent to the following two conditions for tensor F. First condition, this is in differential geometry, it's called three-valiant Kadazzi tensor. Usually in classic differential geometry, I talk about it for students of second course. It's Kadazzi tensor if it's symmetric. Two-valiant. If tensor is two-valiant symmetric tensor with this condition, it's Kadazzi tensor. It's three-valiant Kadazzi tensor. And we have this condition. How to obtain these conditions as reduction of the fundamental equations of the theory of submanifolds? Of course, we should consider these submanifolds with potential of normals. Of course, we should consider not submanifolds with flat normal bundle, but condition 4 is the same. First fundamental form, Gij, of course. Metric is in normal space. We should consider constant. It's the same constant as in associativity equation, Gij. Structure constants of our algebra. And if we consider submanifold with these properties, metric in tangent space, such metric in normal space, such second fundamental forms, and dimensional submanifold codimension n, then we consider exactly these two conditions from fundamental equations of the theory of submanifold. So, of course, it's Kadazzi equation, or Peterson-Mainardi-Kadazzi equations. And this equation is equivalent to the associativity conditions, and it's equivalent to Gauss equations, and it's equivalent to the Ricci conditions for this submanifold. Gauss conditions and Ricci conditions are again coincide in this case. So if tensor F satisfies to these two conditions, then we can consider submanifold n-dimensional submanifold in 2n-dimensional pseudo-Euclidean space with this first fundamental form and this second fundamental forms, and this metric in normal space. So I finished.
Let's send the speaker. Now, the questions.
Sorry, did I understand correctly that if you have this equation on top left, then under certain assumption, this eta can be replaced with the Gaussian, with the Gaussian of f, and then the same equation holds with eta replaced with the Gaussian.
Mish, I didn't understand. Sorry.
So on top left you have
По-русски, да? Скажи по-русски.
уравнение ВДВ у тебя.
Да. Какое уравнение?
Вот
С постоянной метрикой или?
С постоянной метрикой eta.
Да.
Eta is constant.
Да.
Тогда можно заменить eta на Гессиан функции f, и уравнение, то же самое уравнение выполняется при определенных условиях.
Не, ну что значит заменить? Если мы рассматриваем плоские координаты, тут, понимаешь, вот связность, например, если ты рассматриваешь метрику постоянную, связность будет нулевая. Здесь связность не нулевая. Там, и связность дает там решение уравнения. Я не очень понимаю, что значит заменить. Уравнения такие, что если заменить метрику, да, на Гессиан, то будут вот эти новые уравнения вот для этого случая, когда у вас метрика вида Гессиана. Да.
То есть f удовлетворяет и тому уравнению, и другому. И исходному уравнению, и новому уравнению заменить.
Там другая f будет.
Другая f.
Конечно, конечно. Если ты рассматриваешь плоские координаты, там f другая. Если ты рассматриваешь координаты, в которых метрика имеет вид Гессиана, конечно, и то, и другое плоское. Поэтому там могут существовать координаты, в которых метрика имеет такой вид, и метрика имеет такой вид. Если здесь функция f, она этим определяется, там функция f будет другая, когда ты постоянную метрику. Я обозначаю одной буквой, но там будет, надо буквой phi обозначить, например, другая.
Еще вопросы? Any other questions?
This algebraic structure, which is not flat Frobenius manifold, is it an A-infinity algebra?
N-dimensional algebra is.
No, A-infinity. So it's
I don't know. I did not check it. I don't know. It's some Frobenius. By the way, in algebra, consider Frobenius algebra, which are not associated and so on. Frobenius algebra can be non-associated. So it's Frobenius algebra. I don't know about connections with infinity. Maybe it's interesting to understand, to consider, but I don't know.
Also a question. You treated all these structures from the point of view of classical differential geometry.
Yes.
However, Frobenius structure here in Dubrovin theory, quantum homology, from the potential is composed from the Dubrovin.
Yes, I understand.
Related. So, is there some analog of Dubrovin theory from non-flat Frobenius manifolds?
At least I should say that I obtained these equations when I introduced submanifolds with potential of normals, because conditions are very natural here, as you understand. The same more or less as for flat metric and Gaussian metric, but I didn't know is it interesting or not, and where it can be applied. So I was very happy when I found a number of papers about curved WDVV equations, and as I know, there are some different contexts also. First of all, it's supersymmetric multidimensional mechanics, about which Misha Fegin talked here, but in flat, yes, in flat space. If we consider the curved space, this generalization was applied from the WDV equations as physical model in supersymmetric mechanics. There are WDV equations, and there are some natural generalization to curved space there in that model, in that physical model, and there is a number of papers, but I don't know, and some super fluid in fluid, some applications also I have seen, but I don't know any application in Gromov-Witten theory. Maybe it's interesting, but
That's an answer.
yes, it's very interesting. It's very natural submanifolds, really, very natural.
Any questions? Any questions from internet? Yeah, let's send.
Well, may I ask a question?
Yeah, of course.
Yeah, do you hear me?
Yeah. Yes.
Yeah, I'm curious about examples, even about your old result. So we have interesting examples of Frobenius manifolds, and they should correspond to some submanifolds in Euclidean space. Can we compute them explicitly for some interesting examples of Frobenius?
Yes, I wrote some papers about realizations, Dubrovin-Frobenius manifolds as submanifolds of this type. It's a linear equations, partial differential, but linear equations to find radius vector of this submanifold. On radius vector of this submanifold, we have some partial differential linear equations, and it's possible to construct explicit examples. And here also there are some explicit examples for curved WDV equations. There are also explicit solutions. It's, by the way, it's very big generalization of flat WDV equations. It's much more general.
Thank you.
Okay, let's other questions. Yeah, let's speak again. Will be next stop maybe.
Next speaker is Maxim Pavlov, lead the Physical Institute Moscow, New Hamiltonian formalism for semi-Hamiltonian systems of hydrodynamic type.
Thank you very much. Thank you for invitation for me to participate in this beautiful, nice conference. Here I have opportunity to meet my friends, colleagues, and this conference is dedicated to memory of Boris Dubrovin. I know him many years. Of course, we have plenty discussions. I was many times visitor in Trieste where he worked for many years. So I had with him very good friendship and collaboration. Also, we published one common paper about double DDV equation. And now I'm going to speak about a little bit different subject, but also connected in some sense that I'm going to tell you with concept of Dubrovin-Novikov Poisson bracket. So this is a reason for me just to attract your attention again to this famous, in my opinion, result made by Dubrovin-Novikov almost 40 years ago. And I would like just to tell about some alternative construction to the construction presented by Dubrovin and Novikov at that time. So you can just see link between both constructions, and you can see how such interesting geometrical interpretation can appear also in the construction, which you will see in next slides. So I start from, as usual, theory. You can see conjugate curvilinear coordinate nets. This means that I have so-called rotation coefficients beta ik, and they, together with hi, satisfy this linear system of equations. So we can say if we fix beta ik as functions of n independent variables rk, then this system of equations necessary to solve. And since here we have plenty derivatives, dri, drj, drk, etc., we need just to check the second order cross differentiations. Once we do it, we come to so-called Lamé system of equations for three distinct indices. So from this point of view, we can say that this is non-linear system of equations determined by appropriate Lax pair, or better to say Lax representation. So this Lax representation is for this nonlinear Lamé system for rotation coefficients beta ik. So as usual, from such point of view, you can look on this system and say this system is integral by inverse scattering transform. Why we say such words? Because the system has such kind of linear Lax representation. Okay, so simultaneously we can introduce extra vector function psi, write similar linear adjoint system of equations. You can compare this line and this line. So the difference between these lines is obviously just transposition. If I take matrix beta, so this is transposed matrix beta. This is only one difference. And again, if you check compatibility condition of this adjoint linear system, you come back to Lamé system, because doesn't matter how indices are organized in such a system. I'm speaking about linear system of equation. You definitely will come here, and if you change indices, I mean from matrix to transpose matrix.
It's not Lamé system, it's Darboux system. Lamé system is some reduction of the equations. It's
Okay.
Darboux system.
I will.
Lamé system for orthogonal.
Yeah, I will correct. So we have this Lax representation, as I said, according to standard approach. We have this system of equations, integral by inverse scattering transform, because the system has this linear overdetermined system of equations or adjoint linear system of equations. So this system is three-dimensional, and you can just select any three indices and call them indices 1, 2, and 3. So for any three indices, you can write such system of equations. You will have these 6 equations. And from that point of view, this nonlinear system of equations has or this Lax representation or this Lax representation. So from this point of view, we say the system is integral by inverse scattering transform. Once we check compatibility condition, for 3 indices, we come to this set of equations. This is just a simple illustration. So you see, I can replace R1 by X, R2 by Y, R3 by Z. So in X, Y, Z, and these 3 coordinates, I have such 3-dimensional system of equations, integral by inverse scattering transform. Once we change situation slightly, so again, we have 2 Lax representations where every of them determines this, as Alex suggested me to call Darboux system. Then compatibility condition give us, as usual, that system, but now we can equip this pair of Lax representations by the relationship between given linear system, Lax representation, and its adjoint linear system. So you see, this is a very trivial fact, but nevertheless, I would like to again attract your attention that if you have solution of one linear system, this is not enough to construct solution of the adjoint linear system. So in general case, if we have 2 linear systems, linear and adjoint linear system, if we substitute any relationship connecting solution of one system with another one, this means that we will reduce space of solutions. But in such a case, indeed, if we know solution of one system, we can reconstruct solution of another one, and vice versa. So from that point of view, if we add this differential operator first order, connecting solutions of adjoint linear system with solutions of original linear system, then we come checking all compatibility conditions to this extra set of conditions. Better to say, people prefer call it in classical differential geometry in modern language just flatness condition. And we had originally that system of equations in the left hand side. So we have original system of equations that we can call Darboux system, and this set of equations which I call flatness. So altogether, this set of conditions come from restriction of these 2 Lax representation on extra relationship between 2 these Lax representations. Okay, so we say that this system is integral by inverse scattering transform because the system has Lax representation or this adjoint Lax representation, this system is 3D dimensional. However, now I would like to use alternative strategy in comparison with all that people know in theory of integrable 3D or 2D dimensional integrable systems. What I'm talking about. So again, we have this linear system of equations. Let's take 2 particular solutions, which we call HI bar and HI twiddle. So again, we have linear system of equations, and we take any pair of particular solutions of this linear system of equations, any linear pair. Then we can introduce n-component hydrodynamic type system whose characteristic velocities are determined as ratio of these particular solutions. So why I'm talking about alternative approach, exceptional Lax representation? Because I never heard about any possible ideas connecting with any Lax pairs in theory of integrable equations. So usually people say, okay, I have some Lax representation, I check its consistency. From consistency, I come to some nonlinear system, that's all. If I have linear system with variable coefficients, these variable coefficients satisfy nonlinear system. The subject of such investigation is that I need to integrate corresponding nonlinear system of equations. But now I'm speaking about different situation. I have the same linear system of equations. Assume that beta ik already solved. So I made everything that was written in the previous slide.
Then I determine two particular solutions, which I call HI bar and HI twiddle. So finally, I come to integral hydrodynamic type system, but integral by Tsarev generalized holograph method. This is different construction. In previous construction, these coordinates Ri were independent variables. Now they became functions of x and t. So this is different level. Again, I never heard about any similar construction that you see in this slide from that point of view. Previous slide is well known from theory of three-dimensional or two-dimensional integral systems. But this slide, I cannot here. So this slide is exceptional from that point of view, exceptional part of theory. So this way how to go to Tsarev generalized holograph method. Okay, so what is it? I have given hydrodynamic type system. Tsarev generalized holograph method means that some algebraic formula in implicit form describes solutions Ri functions of x and t in this way. So from this system of equations, if such a system is integral, this means integrability conditions are fulfilled. Then solution can be written in this form where zeta I solutions of that linear system of equations where so-called Lamé coefficients according to this diagonal metric coefficients formula are determined by this ratio. So this is standard construction presented by Sergei Tsarev almost 45 years ago. So this classical results made by him many years ago. Now we have this system of equations. We can determine these Lamé coefficients Hi. Then we can determine so-called rotation coefficients that you already saw in previous slides. Then we check integrability conditions, and they indeed satisfy Darboux system of equations. So flatness conditions that I announced before, we can say that this diagonal metric is flat if rotation coefficients satisfy this extra set of conditions, which come from existence of that relationship between one Lax representation and its adjoint one. Please pay attention that here Hi, Hk, psi I here, beta Mi. I am attracting your attention because I am going next slides again speak about these elements of that construction. So technology is following. We can introduce according to this rule partial derivatives of special set of functions A with superscript gamma. Here derivative with respect to this Riemann invariant Ri, where hydrodynamic type system was written in that diagonal form. So in that language, we can determine these coordinates, and then given hydrodynamic type system written in diagonal coordinates Riemann invariant Ri takes conservative form where A, beta are called flat coordinates. This system written in, from this point of view in local Hamiltonian structure form according to construction of Dubrovin-Novikov 1983. So that was a result made by Dubrovin-Novikov 1983. We have such a hydrodynamic type system if the system is diagonalizable. So you can find Riemann invariants, all that you saw in previous slides where I'm talking about Tsarev generalized holograph method. Then such a system has local Hamiltonian structure, and connection between this local Hamiltonian structure and this language I'm speaking about, this flatness condition, this relationship between two Lax representation, this connection is can be rediscovered. Okay, so we have hydrodynamic type system written in diagonal form. This is ratio for characteristic velocities. Hi bar participate in definition of Hamiltonian density H, where Hi twiddle is determined by that right-hand side expression, where everything Hk bar, Hk twiddle, psi I gamma, all of them have the same rotation coefficient. This means that we have common picture that all objects are subject of the same construction. So we have hydrodynamic type system, which is connected with this Darboux system and this flatness condition. This is Laxer representation. This relationship connecting two linear and adjoint Laxer representation. Again, this is old story. Here, nothing new at this moment. Just I refresh memory of everybody who dealt with these constructions, or if you never met such objects, I just would like to again explain such simple ideas. We have rotation coefficients, we have corresponding linear system of equations. Assume that one linear system and another one are connected by first order differential operator. Then we can construct link to hydrodynamic type systems written in local Hamiltonian structure of Dubrovin-Novikov type. And now I'm going to speak about a little bit different picture. So now I just would like to attract your attention before I continue to one important place here. You see di, bik, dk, bki. Here bmi, bmk. This is flattening condition. This is important for my further presentation. So we have Laxer representation determined by this relationship. We have hydrodynamic type system with local Hamiltonian structure. Now I'm speaking about alternative construction. So that you saw before, we have one linear system, a joint linear system, and we have transformation from a joint linear system to given linear system. But now I'm speaking about opposite situation. Please see here. I'm speaking about inverse picture. I have solution of given system HI, and I would like to construct solution of a joint linear problem. So actually, from just pure mathematical point of view, I made nothing. I said, let's call this system as given, let's call this a joint, but I can say change indices and I call them in opposite way. Doesn't matter. Point is that still I would like to keep meaning of all letters absolutely in the same way. So HI belong to language of so-called Lamé coefficients, and psi I from that point of view belong to language of conservation law densities of given hydrodynamic type system. From that point of view, if I check the same conditions I'm speaking about, these two linear problems together with this first order differential operator, then I come to opposite picture. You see, that was the reason why I called di, it was written beta ik, it was written dk, beta ki, it was written beta mi, beta mk. So due to this different first order operator, I come to a little bit different picture. And when I had talked with Sergei Tsarev about this, my observation, he told me, let's call this condition as anti-flatness. Of course, maybe here we can, from geometrical point of view, suggest more better notation. But up to this moment, I would like to use it because I don't know better geometrical interpretation. However, we have two linear system of equations now where solution of given system determines solution of a joint linear system. Then we can ask, is it possible to say anything about such hydrodynamic type system? Is the system Hamiltonian or not? So we know that when we considered previous picture, I'm speaking about this one. Here we know that given hydrodynamic type system has local Hamiltonian structure. But what about this particular case? This case is Hamiltonian. This is unclear up to this moment. What to do in such a case? Or maybe again something happened with, yeah.
Yes, 1 moment. Now it's work. No. Recording in progress.
Может быть, ты можешь что-то сделать?
No. Sorry. Что мы найти приложение, которое демонстрирует саму. Да, я не снимал.
Oh, okay. So the question is such a system is Hamiltonian under this extra restriction? Then let's consider such an example. We have this simplest two-component gas dynamical system. Two equations, density of gas rho, velocity of this gas dynamics u, and this is polytropic gas. So f of rho, in general case that we consider now, is arbitrary function. So from this point of view, this system has one local Hamiltonian structure of Dubrovin-Novikov type for arbitrary function f. So again, if function f is arbitrary, then this system of equations has only one local Hamiltonian structure of Dubrovin-Novikov type that you see here, precisely corresponding Hamiltonian density here, corresponding momentum density here, corresponding functional rho here, and h1 is just u. So this is well-known situation for many also, yes. However, Nutku and Olver observed that this system of equations, again, for arbitrary function f, has also third order purely differential operator b, such that we can construct recursion operator where matrix W is determined by this formula. And how to understand everything here, we need to take this matrix W, we need to differentiate this matrix with respect to x, then we need to take its inverse function, inverse matrix, and then we acting twice by this recursion operator on Hamiltonian operator, again, this Hamiltonian operator of first local Hamiltonian structure, we can construct this third order purely differential operator, which is Hamiltonian for Korteweg-de Vries equation. Oh, sorry, for ideal gas dynamics. So from that point of view, statement is following. We have ideal gas dynamic system with arbitrary dependence on rho. That system, nevertheless, this system has pair of local Hamiltonian structures, where one of them is of Dubrovin-Novikov type, of first order. Second one is third order purely differential operator, second local Hamiltonian structure. From that point of view, we can formulate a list of questions. So how to explain why this Hamiltonian structure appears in that context? Second question, is it possible to generalize construction on multi-component case, because it was only two-component case? Then how to recognize that if we consider more complicated system of equations written in some arbitrary coordinate system of dependent functions, how to recognize that such system can be equipped by this local Hamiltonian structure? How to construct such a structure? How many such local Hamiltonian structures can be found? And is it possible to construct a relationship between these Hamiltonian structures and structures from Dubrovin-Novikov construction? So on all these questions, I have some answers. So key idea is, the point is that we can take this Lagrangian density. And if we will compute corresponding Euler Lagrange equations, then we can compute, should be obvious, some non-local symplectic operator. And the question is, if we have some non-local symplectic operator, how to invert this operator? Actually, in general case, this is complicated task. but not in this particular case. So let's consider the general picture. Previous speaker, Oleg Mokhov, spent plenty time for investigation of this general picture. We have this Lagrangian, which is linear in first derivatives with respect to time variable t. So from that point of view, linear Lagrangian densities in first derivatives of t are so-called degenerate Lagrangian densities. If we have deal with Lagrangian degenerate densities, we should introduce some special procedure how to construct corresponding symplectic and then Hamiltonian structures. Idea is following: we can derive Euler-Lagrange equations. Then we say, if we introduce inverse operator k capital to symplectic operator m determined by this Lagrangian density, so m capital comes precisely from Euler-Lagrange equation. Since Lagrangian density is linear with respect to time variables, it's easy to do. It's easy to express such a operator. However, computation of inverse operator to m capital is not so simple program in general. So in general case, for arbitrary functions gk, this is very complicated problem, and maybe this is unsolvable problem from the point of view that for generic set of functions gk, this is possible to do. So we need to select some special subclasses of functions gk where we are able to do it, where we can at least expect that we shall be able to do. Indeed, let's consider now gk are functions of only two entries, r and rx. Better to say not two entries, two n entries, n variables r and n its first derivative, their first derivatives. So from that point of view, this symplectic operator m will be significantly simplified. So now this is just pure differential operator first order. Then if we add extra assumptions, that let's consider gk not like just some function of r and rx, but where we have set of functions in denominator. In denominator we have rkx, and numerator we have these functions of r only. Then we can this huge expression write in this very compact form. I'm speaking about diagonal terms. If I'm speaking about off-diagonal terms, these expressions will be written in that form of equations. So we now have everything determined: coefficients on diagonal block and coefficients in off-diagonal block. Then statement is following: we can invert that operator. So this is already, you see, non-local Hamiltonian structure determined by this operator k hat. And this operator k, according to this theorem, is, you see, exists if and only if rotation coefficient satisfies so-called anti-flatness condition, where everything could be reconstructed step by step. So we have this so-called structural flows, or some people can prefer call them primary flows. Anyway, we have non-local Hamiltonian structure of that order dx minus 1, while corresponding elements of symplectic structure are determined by just linear differential expressions. So we have that Lagrangian density term, which is linear in time variable tau, term is linear in derivatives with respect to x. These are functions of r only. This is Hamiltonian density h. Euler-Lagrange equations give us this hydrodynamic type system of equations. And this Lagrangian density is nothing precisely but Lagrangian density found by Yavuz-Nutku, written in this form because U and ρ are conservation law densities. They are not Riemann invariants. This means that if you take this Lagrangian density, and if you rewrite this density in terms of Riemann invariance, you definitely come here. This is just particular case of that Lagrangian density. Okay, so mixed local Hamiltonian structures. This structure of Dubrovin-Novikov type, numbered 1. This structure, number 2, is presented at the bottom of this slide. So everything here is for Dubrovin-Novikov case. This is everything for alternative construction presented in that part. So we have from that point of view question, is it possible to consider space of bi-Hamiltonian structures where one of them is determined by these elements, and the first one, this is standard Dubrovin-Novikov Poisson bracket. So from that point of view, if such systems are described, we can construct, of course, corresponding recursion operators. From that point of view, this is local operator, this is local operator. This means that recursion operator also is local. So applying step by step this recursion operator, we can produce infinitely many local Hamiltonian structures here, infinitely many local symplectic structures here. So we have nonlinear system of PDEs that you saw from the beginning. We have flatness condition. Let's now add this anti-flatness condition. Then we can glue all of them together. And from that point of view, we come to corresponding Lax representation, which contains spectral parameter lambda. So now we are in a two-dimensional case, not in three-dimensional case. From that point of view, we can completely investigate this subclass of integrable systems. And following example, which I like very much, we can consider this class of hydrodynamic type systems. You see what is important, in my opinion, here. If I write here plus instead of minus plus, this class of hydrodynamic type system is connected with so-called elliptic coordinates, which are known from the point of view that corresponding set of local Hamiltonian structures of Dubrovin-Novikov type is maximal. N+1 local Hamiltonian structures could be found for such type of hydrodynamic type systems. But now I'm speaking about minus, and statement is very similar. If we have here minus, this hydrodynamic type system has maximum N+1 local Hamiltonian, local Lagrangian representation of that form, linear dependence with respect to time variable t, and here linear dependence with respect to x derivative in denominator. So this is just such an example. This is a list of consequences. You can see here, I am not going to pronounce step by step everything what is written here. However, before I finish my talk here, Misha, what I would like to tell you, for instance, for you, what is interesting could be in this picture. I have this application to, for instance, Yegorov hydrodynamic type system, which is subject of WDV. What is interesting from that point of view, when Dubrovin introduced construction of WDV equations, what was important in his construction? Two ingredients. First of them is flatness, that you see this concept is already included in my picture. Second statement is Yegorov property. Intersection of Yegorov property and flatness condition is 1+1 dimensional system, which precisely WDV. However, if we are speaking about Yegorov case and flatness condition, this means, you see here, beta ik equal beta ki. So these two equations coincide with each other. This means automatically that if I have any hydrodynamic type system, which is Yegorov type and has local Hamiltonian structure, immediately this system has infinitely many local Hamiltonian structures, infinitely many local symplectic structures immediately. So if you take any Yegorov Hamiltonian system and somebody say you, this system has local Hamiltonian structure. Yes, indeed, but also the system has infinitely many local Hamiltonian structures. I finish here. Thank you very much.
Comments? Sorry, questions from Okay, so let's thank the speaker again.
Thank you.
Next talk will be in half an hour.
Okay, thanks. Yeah.
Sorry.
Hello, everybody. Should I start? Or?
Just a second. Okay. Okay, I think we can start. Marcos?
Yes, yes.
Next speaker is Marco Bertola, KP tau function, orthogonality on the real surface.
Thank you very much for the opportunity to speak at this conference in memory of Boris, who was my supervisor many years ago, and also we collaborated in recent years, in fact. Boris always liked theta functions. He also wrote some famous lecture notes that many students have used, and he communicated the passion for theta functions and Riemann surfaces to myself in particular. And that actually, out of that love of theta function and Riemann surfaces and algebraic geometry is born a little bit of this talk today. Now, what I'm going to talk about is contained in these three papers, one of which is already published, and in particular, as you can see from the title, will be in this part, right? Because I'm going to focus on the story of KP functions. And yeah, so let's start from a very small reminder of what are orthogonal polynomials, because that's where the story actually begins. So, as probably many know in the literature of integrable systems, the Toda lattice is deeply related with intertwined with a theory of orthogonal polynomials on the line and also on the circle, etc., which very quickly are described as follows. So you take an arbitrary measure on a real line and you multiply by this formal deformation factor, which depends on several parameters that we call times, and define the moments of that measure and the corresponding Hankel determinants. turn out to be at the same time the kp tau function with respect to the times, if n is kept fixed, and if you consider the dependence both on the discrete parameter n and the continuous parameter.
Could you make your presentation full screen if possible?
I think it is, on my end, it is full screen. I think that's my iPad. I think it is full screen on my iPad. I can't really. I think on your end, maybe you can enlarge. The host should enlarge the. So I'm sorry, but the answer to that is technically I can't. So yeah, okay. Let's see if I put it this way. No, that's even worse. Yeah. Let's see. I don't think there is any thing that I can really. Yeah. No, I'm sorry. I don't see any way. So the orthogonal polynomials are the polynomials orthogonalizing the measure, right? And they satisfy the three terms occurrence relation of this type, Pn plus 1 plus An Pn plus Bn Pn minus 1. And these coefficients, An and Bn, are those that enter the solution of the total lattice equations. So now, there is also there are other versions of orthogonality that are called bi-orthogonality that are used in the theory of random matrices, multi-matrix models. And one such example is the bi-orthogonality on the real line, where you have two measures, and then you look at polynomials in two variables, y and x, I mean, separately variables. So something happened there. Okay. So two polynomials which are bi-orthogonal in this sense, right? These are the degrees of the polynomial in x and in y. Now, on the other hand, as probably people in the audience are keenly aware of, I'm not sure if Igor is in the audience today, there are the algebro-geometric solutions of the Kavam-Zeppetyashvili equation, which are constructed out of algebra geometric data. Right? And the question that prompted those three papers that you've seen before is trying to intertwine, to merge these two worlds, the worlds of orthogonality and the worlds of algebra geometric solutions. There is surprisingly little literature on orthogonal polynomials, or they're not polynomials anymore, of course, orthogonal sections of certain line bundles on Riemann surfaces. There is I point out this paper where it's mostly in the direction that probably wouldn't be interesting for people in this audience. It's more in the direction of approximation. So, but I want to focus on the KP rather than on the integrable theory rather than the approximation theory side of the story. So, for me, probably not necessary for this audience, it would be nice to give at least what I mean by Kp tau function. And for me, a Kp tau function is a function of a formally depending on infinitely many parameters times, T1, T2, etc., that satisfies the Hirota bilinear identity. Now, people may not appreciate this definition because this definition is actually a theorem, right? That comes from, the definition is a different one, and this is a theorem, but it turns out that it's an equivalent characterization, and therefore it's convenient to take it as the definition. So the Hirota bilinear identity is this expression where you recognize here basically this piece is the Becker-Kieser function, and this other piece is the dual Becker-Kieser function. And I forgot to write what is psi, but of course psi of t zt is the formal series TLZ to the L. And this is the common symbol used in this context. So now whatever we do in the end, we have to produce a function of infinitely many times that satisfies the hierarchical bilinear identity. Please stop me if there are any questions. Now, it feels a little bit weird, but I will give a very quick rundown of Ricciardo's construction for the Pepita function. So it starts with a Riemann surface of genus G. Okay, there's a Riemann surface. And then the next piece of data is the choice of a point that I will denote by infinity on the Riemann surface, and the local coordinate, which is defined in a disk around the point, the chosen point, infinity. And it actually is a coordinate such that it tends to infinity when z goes to infinity. So it maps this yellow disk here to the outside of the unit disk in the z plane. And then we have a generic, namely non-special, divisor of degree g. In this case, would be 2 points here. So this is the input of the construction, and the output is a solution of a KP hierarchy. Now, but what is the actual tau function corresponding to that? That is, in fact, it was in the lecture notes of Boris is given as an exercise to verify that this is the tau function of the algebra geometric solution, and it's constructed as follows. You have to construct the two expression. This is a quadratic form. I will not explain in detail what are these coefficients, but they are independent of times. And also these coefficients are independent of time. So these are a quadratic expression and a linear expression in the times. But the really important piece, the piece of resistance, is this part here, where theta is of course the Riemann theta function. Okay. So, and this vector f is a vector in the Jacobian of the curve. So it's a vector of dimension g, which has component, well, this is the vector of Riemann constants. This is the vector of normalized holomorphic differential. And so this part is time independent. And this part here is where the time dependence enters. So it's a linear expressions. And this is the vector of B periods of second kind normalized differential. Okay, and so it's actually, if you never try to do it, it's a very rewarding exercise to, from this definition, well, I didn't provide all details of the definition because I didn't tell what that was deficient, but from this definition to actually verify the hierarchical bilinear identity. Okay, so now what about biorthogonality? Where is this big biorthogonality? Well, let me remind also that there is the Baker-Acchiesa function, which is actually what Igor constructed in the paper directly. Right? It's a function which is meromorphic outside of the. Sorry, let me just copy this picture. It's meromorphic outside of the point at infinity, with as poles at this divisor. And near infinity has this asymptotic behavior with the one here determining unity. So a way of thinking of it is that it is the spanning section of a line bundle L sub t d, so which is just the tensor product of two line bundles. One is a degree 0 line bundle with transition function given by this expression in an annulus, in the punctured disk, and the other is the line bundle of degree G, and that is determined by the divisor. Now, you can twist this line bundle by adding n infinity. What does that mean? What is now a section of these other line bundles? Well, it's a function that has poles not exceeding d at the divisor d, and near infinity behaves like a Becker-Kayser function, but there is an extra power z to the n in front. Okay? Now you do a little gymnastic with Riemann-Roch, and you discover that the dimension of I think I didn't write it, but the dimension of LT n infinity plus d is n plus 1. So why n plus, what is this n plus 1? Is reminiscence of the dimension of the space of polynomials of degree n, right? So the idea is that if I forget about this d in genus 0, then what I'm writing here is just the space of polynomials of degree n. So this replaces the polynomials. And now I need extra data on top of this standard algebra geometric data. And what is that? Extra data is a curve, a path. I don't want to say curve because then there is the Riemann surface is sometimes called a curve. But so you choose a path. It doesn't matter really what, right? Gamma, and a measure d mu on it. And I assume that it's a smooth measure with, so in other words, you can write it as f of z, z bar times dz. Okay. Well, it could be dz plus dz bar, but it doesn't matter. It's just a measure, smooth measure on the curve. Okay, so with this data, I can construct the biorthogonal sections. So what is that? What does that mean? So I take the space, well, the direct sum of all these line bundles. In other words, those are as before, right? Where this t is the deformation parameter, and then I take another set with different values of the deformation parameter, and I define between these two spaces, I define a bilinear pairing by this formula, where the measure and the contour now come in explicitly. Okay, so then you can construct a full set, generically at least, you can construct a full set of biorthogonal section. What does that mean? It means that, well, you take these psi n belongs to LT of n infinity plus d, but not in n minus 1. So it has actually, quote unquote, a pole at infinity of order n. It has an essential singularity, but it has exactly a power z to the n in front. Okay, and similar story for this phi n, and such that they are biorthogonal with respect to this period. How to construct that? Well, you can construct it using a basis of sections that play the role of monic polynomials, like the monic powers. And actually, you can write an explicit formula in terms of the so-called twisted Cauchy kernel, which is the, well, I'm not, if I start explaining it. So it's a Cauchy kernel that behaves like e to the psi of p t minus psi of q t times 1 over p minus q on the diagonal. Okay, near infinity. And it exists, you can write it in terms of theta function. I will write formula here for brevity. So that defines actually exactly, this is a section in LT of n infinity plus d. And but modulo LT n minus 1, infinity plus t. So those they're not orthogonal in any way or shape or form, just some spanning sections. So now you can, out of that, construct the actual biorthogonal sections that in this slide, for some reason, I have denoted by Pn and Qn. Okay, so you build the bi-moments of the measure out of those bases. So you take the zetas for the line bundle LT, the zetas for the line bundle LS, and then you construct these numbers, infinite matrix of numbers. And arrange them into matrices, and in this way, where the last row is the spanning sections up to n, and the result by simple linear algebra is the biorthogonal section. So what that means is that now P and similar expression, of course, for they satisfy this biorthogonality. So now whether can I do that? Well, actually, it turns out that the biorthogonal sections, these Hn, these P and Qs, they exist if the pairing is non-degenerate, right, up to a certain degree of the bundle, and or vice versa, if these numbers, these expression, these functions of TNS that are not zero. These actually, from just elementary linear algebra, they are just the ratio of the consecutive principal minors of this matrix of bimoments. Okay, so for example, this one is H0, this one, the ratio of these two minors is H1, and so on. So what is the tau function? I'll define it now. Okay, so well, let's look at this last line first. So it's a product of the two algebraic geometric solutions of whichever evaluated at different t and s. Well, this is a linear expression, is not so important. The important part is this determinant. Okay? The determinant of that matrix of moments. Of course, it depends on n, and it depends on two sets of times, t and s. Now, if you expand what this definition means, then you just find the first line, right? Where this is the pieces that go into the algebraic geometric function, and this determinant by simple linear algebra manipulation is this multiple integral of two alternants, right? Determinant of functions. So these things are called alternants. Okay, so the gist of the story is that, well, first of all, this tau first it is zero. What gives a meaning of the zero of the tau function? It's zero if the pairing that I defined before is degenerate, or if basically the divisor, well, if this vanishes, right? If these theta functions vanish, which means that basically we are on the theta locus in the standard algebraic solution, but also vanishes if this determinant is zero. Right? And this determinant being zero is simply a statement that the pairing is degenerate. Moreover, it satisfies separately the KP hierarchy in the variables t and s, and also satisfy a version of the two-toda hierarchy. Okay, so that is the outcome. And of course, you realize that for n equal to 1, where basically this is the 0 by 0 determinant, which means 1, then this tau 0 is just the product of two algebraic geometric solutions, well, up to some non-essential factors. Okay. So it's like taking two tau function and zipping them together, right? By using the measure of orthogonality. So here is actually the actual theorem, right? Satisfies the Hirota bilinear identity. It's that, and this is what I mean when I say that it satisfies the two-Toda hierarchy, because in this bilinear identity you have interplay both the shifts in the times and the shifts in the index. Okay. And it's not exactly what Adler-Vermeulen defined, because there is this extra piece which I couldn't understand exactly. I mean, how it enters, how it play, what role it plays, but it's the outcome of the computation. Moreover, the biorthogonal sections that we introduced are actually the Becker-Chiesa functions of these tau function, more precisely. So more precisely, I'll give the statement in the next slide. And this is the last statement, which says, well, exactly what is the meaning of the zero locus of this tau function. In fact, the tau function of integral hierarchies, they are not, they play double role, right? They generate nice differential equations, but most of the time they come from some form of determinant. It's either a finite determinant or a Fredholm determinant. And that means that the locus of their zero has geometric meaning. And this geometric meaning, in this case, translates exactly in the fact that either your divisor becomes special, right? And that, in other words, sorry, not this divisor, the evolution under the flows becomes special, or that the pairing between those two dual spaces of line bundles becomes degenerate. Okay. So so here is the key of the proof of the bilinear identities. It relies on these two propositions, which are actually where the complication lies, right, to prove these propositions. So here is the Becker-Chiesa function, according to Sato's formula, if you wish. Right? So you just do the honest shifts of the times, and then you plug in and see what happens to the expression that I gave. And it turns out, well, now don't be fixated on this part, right? But the key, the x dependence is in here, and this is precisely the biorthogonal section of that line bundle. The rest is more or less normalizations. Notice that also there is the local coordinate to the power n. Now what this delta here is just a delta is a non-singular half integer characteristic in the Jacobian. Right. So notice that this what is omega delta? Well, in fact, I should say the square root of omega. This is omega delta is a differential. Square root is a spinor, and that's a spinor exactly relative to the choice of this characteristic. And as this dividing by these edges makes that into a function near infinity. Okay. The dual Becker function, well, you probably are ahead of me, right, in reading the slide, is that other similar expression, but of different nature. Because while the Becker-Chiesa function is a function, at least locally, the dual Becker-Chiesa function is more like a differential, where this R is obtained by taking some suitable Cauchy transform of the dual biorthogonal section. Okay, so you see explicitly also coming in the measure of orthogonality, and this is the same Cauchy kernel that I alluded to before, which also can be written explicitly in theta functions. Now it has these properties, right? And now because I think I still have maybe 5 minutes, I want to give you actually the proof of the bilinear identity. Okay, so I need this. Okay, and, before I give a proof, I will comment on where these formulas come from. Well, they are consequences essentially of the Fay identities. Okay. Sometimes called the trisecant Fay identity, but trisecant is a special case of hierarchy of Fay identities, which translated in these settings and this notation reads as follows: this determinant of these sections of that line bundle multiplied by the theta function can be also alternatively written as this explicit product of theta functions. Okay, so if I think you must have encountered this kind of identity, but it's the higher genus version of the van der Monde determinant. And if any in the audience have had any experience in dealing with orthogonal polynomials, the person will immediately know that van der Monde determinant is the entry point precisely for the theory of orthogonal polynomials, right? When you analyze the matrix models. And so that is a little bit the conceptual link between the biorthogonality and this word of higher genus algebra geometric solutions. Okay, so I said I kind of oops, okay, I copied the wrong formula, so I think I need to erase that and copy. So I said that I want to okay, so that's one piece of the formula is the Baker-Kaiser function, and here is the dual Baker-Kaiser function. Okay, so there we are. Okay, so now you have to, sorry, I didn't cut and paste it completely very well, but okay. So now you have to simplify pieces, right? So everything simplifies. Well, there will be a determinant that multiplies, but that's not important. This z simplifies, this theta simplifies, this simplifies with that. Okay. And so basically, in the end, you are left with some constant that depends on t's. And then Pn, and also you should take this one for t tilde, right? Because you have to change. So you have Px ts times this fancy Rn x t tilde s divided by dz. Okay, so then what you need to do, right? The Rota bilinear identity says that you have to integrate around infinity the Baker-Kaiser function and the dual Baker-Kaiser function. So I have to multiply this one by dz, so that cancels again, and then integrate around infinity. That's the residue. And then you use Cauchy theorem. You have the integral around infinity. On the other hand, you have this contour gamma. And you have to use the fact that Rn plus minus Rn minus is proportional to Qn minus 1 for x in gamma. Okay. So the integral that you have here by Cauchy theorem is the same as the integral over gamma of the jump. Rn is a differential, okay, with a discontinuity on gamma. So Pn has poles at D, but Rn has zeros at D. So in the product, the product is actually holomorphic away from infinity and has just a jump discontinuity on gamma. And so by the Cauchy theorem, what you're left with, right? If I have here the jump, okay, I replace the jump here, and since Qn is in the span of is in Ls of n-1 infinity plus d, and Pn is the orthogonal section. Oh, sorry, is the orthogonal section. What you're left with is 0. So I go down here, is the integral over gamma of Pn times Qp, then we add the x, t, and s times Qn-1 x t tilde s times d mu, and that is 0 by orthogonality, simply because this one belongs to L t n infinity plus d, and this belongs to Ls, right? Even if there is a t tilde, but it belongs to Ls of n-1 infinity plus d. So in the end, if you have those Becker-Kaiser function on the worked out, the final proof of the Rother relations is really essentially an exercise in calculus on Riemann surfaces. Okay, so now I have, how much time I have? 5 minutes or minus 5 minutes? I couldn't hear that. Okay, so just tell me when I need to stop. Basically, that ends the part on the K theta function, and I will spend the last couple of minutes explaining what has it to do with other notion of orthogonality, and in particular with the theory of Padé approximations on Riemann surface. So the orthogonal polynomials, probably many people will know there, are actually, where did they come from? They came from the Padé approximation problem of writing approximation of Weil-Stilches functions for measures on the real axis. Okay. And so you try to write a rational approximation with ratio of two polynomials. Sorry, this Q and P, this Q has no relation with the previous Q now. And this P, however, is actually the orthogonal polynomial. So these denominators of the Padé approximation are, in fact, the orthogonal polynomial summation. So very briefly, because my time is quickly running out, is that if you want to extend this notion to higher genus Riemann surfaces, what you need to do is to replace this expression. Right? You can still have a contour on the Riemann surface and the measure, but you need to tell me what is z minus x, because on the Riemann surface there are no global coordinates. And so what you do is that you replace, first of all, I multiply the Weil function by dz, so I promote it to a differential. And then I have to generalize this expression, and that is generalized by a Cauchy kernel. There are many Cauchy kernels, they depend on G parameters, right? And each take different form depending on what is your preferred taste. But most likely you want to consider them as function of an external parameters parameterized by divisors of the grid G. Okay, so that now starts connecting with the previous story. And so the logic is that of replacing the notion of Weil function by a suitable Cauchy transform, and this depends on a divisor D of the grid G. And then try to set up a suitable approximation problem where, of course, instead of polynomials, you have to consider sections of line boundaries. Right? And this is precisely the same type of sections that we were considering before. The numerator has to be a differential, so not, and this is the condition, the Padet condition in higher surfaces. And it turns out that this notion is related to orthogonality exactly as in genus 0, which is actually not as trivial as you may think. If you know the proof in genus 0, that proof doesn't work. Okay? So you have to work a little bit harder and use the properties of a Cauchy kernel. Anyway, so I'm going to probably stop here. I just want to advertise this new notion of the approximation on a Riemann surface. And if you are interested, of course, you can just look at the papers I mentioned before. So let me thank again the audience for patiently listening to my rambling, and I will now stop here. Thanks.
Okay, any questions? Sorry, I have a question, because I remember when we worked with Sasha Orlov, we made also introduced discrete times, but we added second point, obtain something total type. And for the log function, we assume that it has pole at infinity extra pole, extra 0 at the second point. The dual function had pole at the second point and 0 at infinity, because in some sense they had opposite devices.
Oh, you mean the Baker-Chiesa function?
You consider different situation. You add infinity to both, to the function, to the dual function.
Okay, right, but so it's so I'm not entirely sure what you are referring to, but what I'm saying here is that it's not a choice, right? Because the moment I tell what is the tau function, right, and I give an expression in terms of theta function, yes, then the Baker-Chiesa is that, right, e to the, and the dual is that. And so what comes next to the minus zeta and plus zeta? Okay. So okay, psi and psi. So then it's not my choice what these two objects are, right? Because they are completely determined by the tau function.
Well, that in discrete times. By the way, do you assume that those functions are functions, or you assume that, like Ricciverdi, psi was function, psi star was differential, or they both may be spinors?
It's really a matter of taste. You can move from one. So the only difference I can tell you where exactly. So you seem to be very well versed in this story. So the only difference, just a second, is as far as I remember, if I put this q here, then psi is a function and psi star is a differential. If I don't put the q, or I put, I forgot, 1/2 of q, then they're both spinors. But that comes out of the computation itself. I tend to stay away from spinors because most of people don't like them. And, but yeah, it's it doesn't make a substantial difference whether one is a function and one is a differential or both spinors. It's just a slight, tensoring by half differentials, semi-canonical bundle.
Yes, you are right. That there is no big difference when you keep the surface fixed. The difference goes into game when we deform the Riemann surface. Then it's difference between functions.
Yeah, of course. Right. Now, of course, I'm not considering the deformations of the moduli of the surface. Actually, that is quite an interesting question. What differential equation one can find in those cases, right, for the tau function?
Okay. Sorry. Any other questions?
In your constructions, your divisor D is generic. Is it possible to say precisely for which?
Non-special.
So
I see. ID equal to Z.
I see.
I mean, this is the index, right? So there are no, in other words, there are no holomorphic differentials with zeros, no non-trivial holomorphic differentials with zeros at D.
Okay.
Is it correct? It's the smallest meaning that the solution of KP is locally regular.
Yes, locally, yes. So near zero, that guarantees that the solution is regular. That's exactly correct. Yeah. So if then you want also to, I don't know, discuss real solutions, then of course you have to impose additional constraints like that the Riemann surface has an anti-holomorphic involution and actually in my setting with the orthogonality, I did that in another paper where you take the anti-holomorphic involution, the contour is fixed, the contour of integration, the measure is real measure, and then you can really start tasting analysis because you can construct these orthogonal sections and study the asymptotics as n goes to infinity, right? And that's what I did in the separate paper. I did it in an example in genus 1, but the theory works in arbitrary genus, and it's based on the fact that those orthogonal sections satisfies if you arrange them into something like psi n minus 1 and some Cauchy transform, satisfy a 2x2 Riemann-Hilbert problem on the Riemann surface. Okay. All right, I'm sorry.
Okay, any other questions? Okay, let's end the speaker.
Thank you very much.
And the last talk of today's session will be in 15 minutes.
Здравствуйте, Искандер Асанович.
Здравствуйте.
В итоге у вас получится запустить презентацию с вашей стороны?
Ну, и давайте, если вылетит, Ну, впрочем, давайте лучше так. Действительно, у меня там связь плохая. Я буду говорить следующую страницу. Окей?
Да, ну, в общем, как бы я вас на всякий случай продублирую. Если вдруг у вас не будет работать, у нас тоже будет открыта эта презентация, я смогу в любой момент заменить вашу презентацию с нашей стороны.
У меня не работает еще. Давайте так. Окей. Let us start my talk.
Подождите, только у нас еще 15 минут.
15 минут перерыв.
Да.
Понял.
В половину начинаем.
Понял.
Искандер Александрович, вам еще, наверное, на одном из двух устройств стоит отключить микрофон, чтобы не было
проблем с фоном.
Искандер Асанович, вы нас слышите?
Да, не одинаково.
Искандер Асанович, слышите ли вы меня?
Да, да.
Здравствуйте. Вот тут Денис советовал, у вас два устройства, правильно?
Да, я сейчас второй мобильник выключу.
На одном из них звук, да, хорошо бы выключить, потому что вот...
Я выключил его вообще.
Понятно, хорошо.
Все, я попытаюсь, видимо, сейчас работать с компьютером. Я тут собирался с вами так, по вашей просьбе. Хорошо.
Хорошо, сейчас где-то... Сейчас уже будем всех звать, чтобы начинать.
Да.
Одну секунду. Нет, еще не начинаем, еще 5 минут.
let's start our final talk of the conference. Is compared by one of creation of similarities of 2D solid called equations represented by A, B triples.
Okay, can I start?
Yes, of course.
Okay, first I would like to thank organizers for inviting me to this conference and giving me the possibility to give a talk on the subject which is closely related to Boris Dubrovin. Traditionally, it's before introduction of LAB triples, the soliton equations were assumed to be equations which have Lax representations. The classical one is the Lax representation for the famous Korteweg-de Vries equation from which started all soliton theory. And such a representation do exist for other one-dimensional soliton equation. Probably better to say 1 + 1 dimensional, one special variable plus one temporal variable. For all such equations integrated by inverse scattering method. They are represented by Lax pairs. So we have two ordinary differential operators, L and A, and the equation is equivalent to the condition that the derivative of L in T in the temporal variable is just the commutator of two ordinary differential operators L and A. For instance, for the KdV equation, we had for L the classical Schrödinger or Sturm-Liouville operator, and A is the differential operator of the third order. These evolutions preserve the spectrum of the operator L, deforming it as follows. So they have a psi, the formally eigenfunction, because I wouldn't speak about special functional spaces. And if psi at the initial moment satisfies the equation L psi equal E psi, then every solution of the equation psi t plus A psi equals 0 at any moment satisfies the same equation, where in the operator L we consider the potential U at the time t. So that's so this equation is just explanation why the spectrum is preserved. LAB triples were introduced by Manakov in the middle of 1970s. They have the following form. So again, we have a L operator, which is not ordinary but partial differential operator, and its derivative in T is just commutator of two operators L and A, plus the product of operators B and L. There are B and A are partial differential operators. The spectrum is not preserved, except its zero level, which evolves as in the case of Lax pairs. Actually, this reasoning is reduced to them is the same as for Lax pairs, because then we introduce substitute psi into the right-hand side of the LAB triple form, we get B L psi equals 0, and so that's everything will look as in the case of Lax pairs. The first non-trivial example of LAB triples, because actually LAB triples were introduced by Manakov in a short known in the Russian Mathematical Service, which probably was not even translated at this time into English, in which he said that it was quite complicated to find non-trivial Lax pairs for partial differential operators. But one can do that if we consider LAB triples. But the first non-trivial LAB triples was found by Novikov and Vasilov in 1984. It is this equation, which in one-dimensional limit reduces to the KdV equation. One-dimensional limit that the complex variable Z, the potential U, which depends on complex variable Z, it depends only on the real part of Z, on X. This equation was derived in the framework of two-dimensional Schrödinger operators, which are finite gap on one level of energy. And such operators were introduced in a short article in Doklady of Soviet Academy in 1976 by Dubrovin, Krichever, and Novikov. At this time, the problem of distinguishing the spectral data, similar to one which were discussed by Marco Bertolo before, finite gap spectral data, similar to one which were discussed in the previous talk, all these devices, the marked points on the Riemann surface, and so on. The problem to distinguish which spectral data leads to potential operators, just operator d bar plus u. It was unsolved until 1984, then it was solved by Novikov and Vasilov. And in the next article, which was published as the first one in Доклады of Soviet Academy, they introduced this operator which preserves this spectral data. And in one-dimensional limit gives a KdV equation. So this is a two-dimensional generalization of the KdV equation, which is different from Kp because in Kp, the special variables x and y have a very different meaning. And here, x and y, they're kind of play the same role. I would like to mention is the modified Novikov-Veselov equation, which was introduced by Bogdanov in early 90s. Bogdanov was a student of Monakov who proposed him this problem, as Monakov told me. And why it's called modified Novikov-Veselov equation? Again, this equation is related to the spectral problem for Dirac operator. Here is a two-dimensional 0 d minus d bar 0. This is two-dimensional Dirac operator plus potential, which is assumed to be real valued. Also, MKdV is related to the spectrum problem for one-dimensional Dirac operator. And that's in difference with the KdV and Novikov-Veselov, which are related to Schrödinger operators, one and two-dimensional. KdV to one-dimensional and Novikov-Veselov to two-dimensional. And then the third equation, which I would like to mention, is the Davis-Stearson equation, Davis-Stearson 2 equation. In this case, it's related to the Dirac operator, which in this case is more general form. U, the potential U, is not necessarily real valued. Again, we have the constraint, as in all these equations, MKdV, M and V, NV, and it's V z bar equal to squared modulus of U over Z. And to be more careful, I have to say this is equation is called defocusing, Davis-Stearson equation, because we have to distinguish two equation focusing and defocusing cases. This equation has a physical meaning. It was first introduced by Davis-Stearson at the beginning of 1970s in the framework of hydrodynamics, in a physical article. And the two previous ones more mathematical. I would like here to return to the contribution by Boris Dubrovin, because then Novikov and Veselov introduced the equation. My teacher, Professor Novikov, proposed me to prove the analog of the Dubrovin theorem for theta functions of prime varieties of two-sheeted covariance of Riemann surfaces with only two branch points. In this case, the prime variety is principally polarized. At the end of 70s, Novikov introduced his famous conjecture that the existence of theta formulas for special kind for introduced actually for Kadamtsev Petvashvili derived by Krichyver in his famous article. Existence of these formulas as solutions for Kadamtsev Petvashvili equations distinguishes the Jacobians among principally polarized abelian varieties. So if such formula exists, then theta function relates to the not to general principally polarized abelian variety, but to Jacobian of some algebraic curve. So the problem, the first partial result in this direction was obtained by Boris Dubrovin in 1982. Then he proved this conjecture modular reducible component. So he proved that really this condition distinguishes in the modular space of principal polarized abelian varieties the subvariety of the right dimension, and one of them contains Jacobians. Probably there are other components. The last case was resolved by Shorter, who proved that there are no other components, and hence completely finished the original Novikov conjecture. Later, in another framework, in the beginning of this century, Krichyver had shown that already the existence of eigenfunctions, Bloch eigenfunctions, which satisfies the linear problem, that already distinguishes the Jacobians among principally polarized abelian varieties. But at this time, in the beginning of 80s, only this partial result, but actually the first strong confirmation that the Novikov conjecture is true, and these soliton equations are strongly related to geometry of abelian varieties, was obtained by Dubrovin. And I managed to prove analog of Dubrovin theorem for premians of these coverings, also modular reducible components, and using Novikov-Veselov equation instead of KP. So it appears that Novikov-Veselov equation also strongly relates to algebraic geometry of abelian varieties. For that reason, I remember that I had to read word by word two famous articles by Boris Dubrovin, his survey in Russian mathematical surveys, theta functions and nonlinear equations, which is probably still the best introductory exposition to this to the finite gap theory, and his article from Izvestia in 1982. And now I am going to the main subject of my talk, the Mutar transformation. Mutar transformation is two-dimensional version of Darboux transformation, which was actually introduced by Mutar before Darboux. He introduced it in the framework of projective differential geometry. And last 15 years, since 2008, the Mutar transformation started to be applied to solving problems concerning two-dimensional soliton equation. We started that with Sergei Tsarev, who taught me the classical Mutar transformation. And there are some other articles, and now that's I mentioned only three results which I would like to discuss here. But among other contribution to this spectral theory, I would like to mention articles by Petr Grinevich and Roman Novikov, who also applying, but to different problems, the Mutar transformation, two-dimensional Mutar transformation, and its differentialization for Dirac operators. The Mutar transformation originally was written for Schrödinger operator. At this time, it was called Mutar operator in projective differential geometry. It was not d bar, but it was hyperbolic operator dx dy plus u. But since it's analytic, we can x and y replaced by z bar. So it's complete analytical stuff. And for all these equations, which I mentioned above, by using Mutar transformation, we're constructing solutions which lose their regularity. The initial data are smooth and fast decaying. Solutions are rational. These solutions are rational because this is specific of this. Probably could be obtained more complicated, but it was enough to obtain rational solutions by this transformation, much less computations. And at a certain critical time, this solution becomes singular. So the regularity of the Cauchy problem for this equation is a special question. So it needs to distinguish special initial data for which the solution stays regular. And now, as I understand it, studied some articles. For Novikov-Veselov, we did it with Sergei Tsarev using classical Mutar transformation. For modified Novikov-Veselov, that was done by myself in 2016. I used the transformation, I don't mention, by some physicist from China. Then the main thing here was to understand that this analytical formula actually is related to surface theory and has very simple geometrical meaning. But for that, it was necessary to rewrite it in different terms, in the terms of surface theory. And recently, actually, the article appeared on arXiv probably last week or this week. I put it there, Davis-Stewartson 2 equation, defocusing equation. Their transformation used for modified Novikov-Veselov and Davis-Stewartson 2 are based on the spinor representation of surfaces in 3- and 4-dimensional spaces. The transformation, the version of Mutar transformation for Davis-Stewartson 2 equation was derived in my article, but the previous, which was preceded by my article with my student Roman Matuev, who decided not to resume study in mathematics, or to extend the Mutar transformation for Dirac operators coming into the representation of Davis-Stewartson to transformation of solutions equation. It's I had to do myself. It took a lot of, for that it was necessary to do a lot of computations. What is the Weierstrass representation of surfaces in R4? This is generalization of the similar representation for R3, but it involves two Dirac operators. This Dirac operator, original one, which comes into the Elabet triple for Davis-Stewartson equation, is formally conjugate. There we swap on this non-differential part. We swap u bar by places. So we have two solutions, psi and phi, of these equations. Then the following formulas define a surface in R4. That was shown by Konopelchenko at the end of 1990s. For this surface, we can write down in terms of psi and phi the metric and the potential u.
Iskander Hasanovich, we cannot hear you.
Hello?
Yeah, now we can hear you once more. No, we can't. Iskander Hasanovich? Iskander Hasanovich?
А вы же ему в чат можете написать, да?
Sorry, it seems that we have a connection problem for the speaker.
That's okay?
Yeah, now we hear you and see your presentation.
Yeah. Thanks. Yeah, because you see connection. Something is with my Wi-Fi. So what is it? Take the real part of z, z1, zn. This is the vector x1.
Iskander Hasanovich, we do not hear you.
But I'm speaking. Now do you hear me?
Yes, now we do hear you.
Yeah. So they take the real part of z z1, zn, and form the vector x1, xn, and take the imaginary part, y1, yn, and form the vector y1, yn. So this have two vectors. Yes? What does it mean that for these vectors, what z lies on this quadric? The real part of this means that these two vectors do have the same length. This is z1 squared plus z. Okay, this is the real part of this equation. The imaginary part of this equation
Iskander Hasanovich, we do not hear you. Показать, что он говорит, кстати. Интересно. Iskander Hasanovich, we do not hear you.
Yeah, I understand, but
now we do.
No, yeah, you do. Yeah, okay, that's the problem. Yeah. So they have two vectors, x and y. One is formed from the real part of z, another from imaginary part of z. The real part of this equation of the quadric means that these two vectors have the same length. The imaginary part vanishes if these two vectors are orthogonal to each other. So these two vectors, x and y, define the oriented two plane. But if we rotate this vector x and y by
Iskander Hasanovich, we do not hear you once more.
Of unit model.
Now we do.
Now they do, yeah. So okay, so we have to go to the homogeneous coordinates z1, zn, and after going to the homogeneous coordinates, we think that it's this vector z, zn up to this relation, up to multiplication by complex, non-trivial complex numbers, give you the parameterization of this Grassmannian. So the Grassmannian of two planes in Rn is just this quadric. So the map z, which is mapped to dx1
Iskander Hasanovich, we do not hear you.
Now, do you hear me?
Yes, we do.
Yeah, now I do. Okay. Because I'm speaking from a cell phone. Probably too loud. Yeah. Okay, so this mapping, then z is mapped to the derivatives of the x1, xn over z is just the Gauss map. For n equal 4, this quadric is diffeomorphic to two products of rational curves. This is the famous diffeomorphic Segre mapping. It's written here in coordinates. So if we have the Gauss map of the surface in R4, written as in this form, as the mapping into this quadric. So the spinors P and phi are of this form. But in difference with the three-dimensional case, in which case the quadric Q3 is just CP1. In difference with the three-dimensional case, phi and psi are defined up to non-trivial gauge transformations. So we have multiplied psi1 by EH, where H is holomorphic, here AH bar, and here it's another one. And the potential is defined up to this multiplication. So since we are working on universal covers of the curves, which can be converted into immersions of the compact manifolds, we can prove that every surface in R4 has a global Weierstrass spinor representation. Why the spinor representation do exist only in these dimensions 3 and 4? It's because the quadrics Qn have no such rational parameterizations if n is greater than 4. This is fact from algebraic geometry. It's very non-trivial curves. They're not products of rational curves. And what are now the DS2 deformation of surfaces, which Konopetchenko introduced in the same article? It is as follows. Since the Dirac operator ethers elabit triples, Konopetchenko proposed to construct soliton deformation of surfaces in the following way: psi t equal a psi, phi t equal a v phi. They give a deformation of the Gauss map. And from the Gauss map, we can define a deformation of the surface up to translations by RT. So at every moment in time, we have the surface defined up to translations. Such deformations also depend on resolving this constraint. Here needs to be careful. And one can do a deformation globally such that it preserves the integral of the squared norm of u, which is up to a multiple just of the Wilmer function over the surface. So the Wilmer function plays the role of the first integral. For Mutar transformation of the surface, let us rewrite this Weierstrass representation in a very similar form. So this S is the surface, then it depends on
recording in progress.
Here the quantities, I'm just writing the formulas by Konopetchenko in very different form. And so if they substitute these quantities here, you see this is just d, integral of d of these quantities that's with matrix where x1, x2, x3, x4 are coordinates in a form, Euclidean coordinates. In this case, we consider the surface as a surface which lies in quaternions. And what is the DS2 deformation? So we can take this deformation carefully, distinguish, because it's the surface is defined up to translation RT. So we have to take the branch of RT, and for every moment of time, take the Möbius inverse of this surface. So if we have surface S, we can take S minus 1. What is it? This would be the Möbius inversion of the surface, plus and the composition with the reflection with respect to the x4 axis, which is which corresponds to real quaternions. And now the Mutar transformation is as follows. Given a surface with a conformal parameter, we may define its potential u up to gauge transformation, actually. But we can define it. The Möbius transformation is conformal, and hence if they get the conformal parameter z on a surface, the same parameter z would be at this Möbius inverse. So this we take S parameterized by z, take S minus 1 parameterized by z, z would be conformal parameter on S minus 1. And now the Möbius transformation is transformal. We take the right branch of this ds deformation of the surface, and at every moment we consider the Möbius inversion of the surface and take its potential, which corresponds to the same parameter. The formulas are quite large, but geometrically they're very simple. And what we obtain that this is new potential also satisfies Davis-Stewardson 2 equation. And what's the meaning now? we have a surface. Take the simplest one. And we consider it's this deformation. So the surface moves in R4. At every moment we take its inversion, Möbius inversion. At the moment then the surface crosses, passes the origin. This origin by Möbius inversion is mapped to infinity. And exactly at this moment, the potential U loses regularity. Because its finity is mapped to, okay, it's not a finite point of C2. So that's, I consider it the simplest example. It is known that if we consider R4 as C2, then every formula, with C2 with two coordinates, complex coordinates Z1 and Z2, that every surface of the term Z2 equal f of Z1, there f is holomorphic, gives you the minimal surface in R4. I think actually these surfaces were introduced at the beginning of 20th century. The surfaces were coined by some name, which actually I forgot, but this is actually the first examples of minimal surfaces, which were found in the end of 90s. And the special properties of these surfaces were discussed by Eisenhardt in articles in Annals, which was published 120 years ago. You can find it in the internet. But it's very simple to see this surface is minimal. But it has many other interesting properties. So what means how looks like the Davis-Stewartson deformation of this minimal surface? It is as follows. We still consider the graphs, but f has to satisfy this equation df over dt equal I and the second derivative of f over z. So this is if they take this graph of minimal surface, although its potential is 0, because it's minimal surface and potential u is 0, the Davis-Stewartson equation is still non-trivial. It gives this deformation of the graph, and then they take the inverse and get the following solution: u is equal I zf prime minus f divided by modulus z squared plus modulus f squared. V is another formula, and this pair u and v satisfy the Davis-Stewartson equation, second Davis-Stewartson equation. That's it. That's how it looks like. The simplest example. No, not the simplest. There are simple examples of the polynomials of less order. Consider f z4 plus c. This is the graph of the fourth power of z. Then this is its deformation with respect to Davis-Stewartson. And then u is the solution of Davis-Stewartson equation obtained after the Möbius deformation. It becomes single at the time c equal 12 t squared.
Your screen presentation.
Yeah, I know, no, it's connecting. Do you hear me?
We don't see it yet. But we hear you well. We hear you well, yeah, but we don't see your presentation or your second account. It's not connected. Do you need me? If you want, I can show your presentation.
Can you show my presentation? There are just last 2 pages.
Give me a second. So please tell me where should I stop?
Yeah. Stop here. Not okay. Before. Previous. Okay. This is the simple formula. One of the simplest formula. You see, then C is complex. The solution is non-singular. Then C is real. Then for time C equal 12t squared, it has singularities. Then C is positive. It has singularity of the following form: u is not has different limits, then we are coming through different directions at point z equal 0. So at point z equals 0, it has one point singularity, which appears exactly at one moment in time. And then after this moment in time, the solution gains regularity again. Since you see this solution is non-singular for C simple complex, so this singularity is not stable, but it's very special singularity. What is interesting? We know that the integral at square u squared, there is the Wilmer functional integral of u squared of the models u squared over the surface. This is the first integral of the equation. So we can say that this quadratic functional has to kind of persist against the appearance of singularities because it's a squared L2 norm of u. For t non-singular types, this functional is equal 4 pi. Then at singular moment it's equal 3 pi. And then it's against regularity, it's again 4 pi. What's the explanation of that? This is the Wilmer functional. When they take the minimal surface and take its inverse, Möbius inverse, we get Wilmer surface. So these are Wilmer spheres with branch points. And for them, the value of the Wilmer functional is quantized. It's a multiple of pi. So for this moment, we get, for the singular moment, the inversion will be Wilmer surface with another kind of branch points. And just for one moment, the first integral jumps to 3 pi and then gains its previous value. And that would be for all other cases. This effect I did find for the modified Novikov equation 5 years ago, but probably I never spoke about this on any conference. First of all, because that's this equation has no physical meaning. It's interesting from the point of geometry, but it has no physical meaning. But here, this is the focus in Davis-Stewart equation is physical. It comes from hydrodynamics, and we see that some of the special kinds of singularities can appear for this equation. Actually, I would like to say that the singular solutions for this equation were known from beginning of 90s. Ozawa found, mathematician from Japan, found the solution which has a blow up. So at some singular moment in time, the solution tends to the Dirac distribution at one point, at the origin. And then it gains regularity again, just at the very next time. So just it's singular exactly at one point at the dot time. As I understand that this scenario or these solutions, its genericity is studied by Christian Klein and his collaborators. And Christian Klein, as I understand, was one of the closest collaborators of Boris Dubrovin at the last year. But in our case, the singularity is not a direct distribution. It's a very different one. And what happens with these equations? What is this? We started to understand the creation of singularity for Novikov-Veselov equation and did numerical experiments with my student Aydos Adilkhanov from Kazakhstan. We even published this article in some communications of nonlinear side and numerical simulation. We demonstrated numerically that for singular solutions of Novikov-Veselov equations, some negative eigenvalues tends to minus infinity as t approaches the singular time. There was a numerical experiment. But for all constructed singular solutions which we obtained by Mutar transformation, we have the following. As t approaches the singular time, the solutions of the equation for the zero level eigenfunctions become singular. What does it mean? So although we are saying that the zero level spectrum is preserved, so that because eigenfunction has to satisfy this equation, there are cases then the eigenfunctions, this point of the spectrum disappears because function psi gains singularity. So in all these three examples for all this equation, there is one general point. The zero level spectrum is not preserved. At some moment of time, some points of the zero level spectrum, it's discrete spectrum, actually it's a zero level, but it's discrete spectrum, disappears, and then solution gains singularity. So this is some kind of specific property of all these computations, which I would like to discuss and mention in my talk here. And I would like that here I have to stop, and thank you for your attention.
Okay, any questions?
Iskander, I have two small questions. First of them is following. You considered a polynomial solution for this linear equation for function f small. So it was, I guess, first example, I'm speaking about fourth order. So you can continue such a consideration.
Yes. Actually, the first examples appears with the lower order.
Mm-hmm.
Yeah.
So
I can continue.
Yeah, and computations looks not very complicated. So
no, not very complicated. No.
Yeah. And second
but
question,
we can consider more complicated minimal surfaces.
Yeah.
Here, consider the very special class of minimal surfaces, the simplest one, just graphs of holomorphic functions.
Mm-hmm. And the question is, you concentrated on Davis-Stewartson 2, but it looks like formally you can apply the same technology for Davis-Stewartson 1. It looks like, I guess, situation is different from the singularity point of view. Is it correct?
That you see, that's what means singular to the Davis-Stewartson 1, Davis-Stewartson 2. My scenario is geometric. We have the inversion of the surface in A4. So for that, it needs to relate this equation to surface theory. I don't know how all the other Davis-Stewartson equations, DS1, are related to surface theory, because in this case, the Dirac operator is anti-diagonal, has dx minus dy. In my case, d minus d bar. Am I correct?
Yeah.
Probably analytically, we can get the same. Probably, if we just extend analytically these formulas from z bar to xy, we shall do the same. That's true, but the simplest continuation analytical doesn't give you initial fast decaying solutions. Because z is replaced by x squared another. So we can do that analytically. I tried to do that analytically for simplest polynomials, but the decay was not very strong. So the singularities was not pointed. But probably with other analogs of minimal surfaces, other formulas more complicated, we can get the same for DS1. They're similar solutions.
Thank you. Other questions?
Do you hear me? Iskander.
Yes.
No. I think you should discuss it with Zheny Kuznetsov, who is very interested in such solutions, and he's very good in, how to say, in the understanding possible applications. That is.
Yeah, because it's hydrodynamics. Yes. I shall do. I shall follow your advice.
Okay, one more possible application is Iskander, maybe.
Yeah.
Okay, a long time ago we consider reduction of Davis-Stewart-Sonic to equation to Liouville equation, and there were more complicated singularities in this reduction of solution on algebraic curves on that plane. So it's such point singularities are not not the only singularities which exist in this.
Yeah, I know.
For this system, it can.
Yeah.
Okay, I just wanted to mention this. Okay.
Other questions, comments? So let's keep the speaker.
Thank you very much.
The conference is over.
So many
Thank you.
thanks to everybody for participating.